Hi everyone and welcome to this Android development course with Java. My name is Martin Yanev, a professional software engineer and a computer science professor at Fitchburg State University. Today I will show you how to write reusable, object-oriented Java code that connects with the system hardware and software. We're going to jump straight to building applications, and in your very first project you're going to build your first Android app. I will show you how Android works under the hood. We will talk about Android APIs. We're going to build a lot of projects, and I will show you how to set your development environment with the Java Development Kit or JDK. By the end of the course, you'll learn how to create Android apps and how to run them on emulators or devices. Make sure that you watch this course until the end, and if there are parts that are not clear, please stop the video, try things yourself, and then continue. You can also drop down a comment. I usually respond to all the comments written under my videos, and I will be happy to help you out. Now please make sure that you like this video and subscribe to my channel so I can upload more free courses like this one. Also make sure to check out the Git repository linked in the description, where you can find the full code for this course. Thanks for watching, and now let's jump straight.
Welcome to our tutorial on setting up your development environment for Android app development. In this video, we'll explore why Android is a fantastic platform, the interplay between Android and Java, and then dive straight into setting up the tools you'll need to start developing your first app. First off, you might wonder why Android is such a big deal in the world of app development. With over 1 billion devices and an incredibly diverse user base worldwide, understanding and harnessing Android's capabilities can open up a wealth of opportunities for you. Android's versatility allows for applications ranging from simple games to complex enterprise solutions. What makes it even more intriguing is how Android and Java complement each other seamlessly to create applications that are not only powerful but also efficient. Now let's break it down. When you write an Android application, you write it in Java, which is an object-oriented programming language. This means that you can create reusable code components, making your coding process more efficient and organized. Once you've written your code, it gets compiled into something called Dalvik Executable DEX code, which is the format that the Android operating system understands. This process takes place in a virtual machine designed specifically for Android, which is known as the Dalvik Virtual Machine, DVM. Before we can start creating amazing apps, we need to set up our development environment. To do this, let's discuss the two key components we need: the Java Development Kit, JDK, and Android Studio, which integrates all the tools necessary for Android development. First, let's download and install the JDK. It's a straightforward process that can be done in just a few clicks. 1. Visit the Java JDK downloads page at Oracle's official website. 2. Choose the JDK version appropriate for your operating system. 3. Download the installer and run it. Once you have the JDK installed, the next step is to configure your system to recognize it. This is done by setting the path variable. You can do this by going to your system settings and adding the JDK's bin directory to the path. This might seem a bit daunting, but don't worry, everyone's been there. To set the path variable for the Java Development Kit, JDK, follow these steps to ensure your system can recognize Java commands and run Java applications smoothly. Begin by accessing your computer's environment variables. Look for the option to edit the path variable within the System Variables section. This is where you will specify the directory that contains the Java executable files, enabling your system to locate them from any command line prompt. You will need to add the path to the JDK's bin directory, specifically C/program files /java /JDK1 80xxx/bin. By appending this path to the existing entries, you ensure that your system knows where to find the necessary executables whenever you execute a Java command. It's important to separate this new entry from the other entries using a semicolon. This distinction helps to clearly separate each path in the list, avoiding any potential confusion. Once you have saved the changes, your environment will be configured to run Java applications, setting a solid foundation for your upcoming Android development endeavors. After setting up the JDK, you're ready to dive into Android Studio. Android Studio is your integrated development environment IDE, where most of the magic happens. It's the platform that allows us to write, test, and debug our Android applications. Now let's install Android Studio. 1. Go to Android Studio's official site. 2. Download the installer specific to your operating system. 3. Run the installer, and during the installation process, make sure to accept the default settings unless you have specific needs. During installation, you might be asked whether you want to install Android SDK, which is essential for building Android apps. Choose to install it since this bundle includes everything you'll need to develop Android applications. Once the installation is complete, you'll be greeted by the Welcome to Android Studio screen. This interface is user-friendly and designed to help you get started without much hassle. Go ahead and click on Start a new Android Studio project. When prompted to choose an application name, go with something simple like Hello World. This name will show up as the app title on your device. Also, remember to set a company domain, which you can put as example.com. Each application you create gets a unique package name based on the company domain and application name, so it will look like this: example, Hello World. Now decide on the target Android devices. The default settings should be fine for most users wanting to develop applications for phones and tablets. Next up is the minimum SDK selection, which determines the lowest version of the Android operating system that your application can run on. For beginners, selecting API level 16, Jelly Bean, or higher is usually a safe bet since it supports most devices while still being relatively updated. Now we're getting into the nitty-gritty of the activity class. Every Android app needs at least one activity, which is essentially a single screen with a user interface. When prompted, select the Empty Activity option. This provides a clean slate to start coding up our interface. Now let's examine how to set the layout for our activity within the onCreate method. To bind our Java code with the XML layout, we write a single line: set content view, our layout, activity main. This method call is crucial as it instructs the Android system to load the user interface components defined in the activity main XML file located in the res layout directory. By referencing our layout activity main, we are using the resource identifier generated by Android, which links to the specific layout file created during the project setup. This connection between Java and XML is essential for the application's user interface. With this line, we essentially tell the application, this is the layout I want to display to the user when the activity starts. It activates the visual elements defined in XML, allowing us to interact with them in our Java code. This integration of XML for layouts and Java for functionality forms the backbone of Android development, enabling a clean separation of presentation and logic. Next, we will explore how to customize our layout further by adding user interface elements like buttons and text views. Now let's see how we can create a simple user interface component in our Android application using XML. In the *res layout directory, the activity main XML file serves as the blueprint for our app's user interface. Here, we'll add a text view, which is a fundamental UI element that displays text to the user. To implement this, we will write a line of XML code. We start by defining the text view tag, which specifies to the system that we want to use this component. The attributes Android layout width and Android layout height are set to wrap content, which instructs the system to size the text view according to the content it holds, rather than to a fixed size. This is essential for ensuring that our UI remains flexible and can adjust to varying text lengths. Lastly, the Android text attribute is where we set the actual content to be displayed. In this case, we'll show the phrase "Hello, Android" on the screen when the app is run. This small yet powerful code snippet integrates seamlessly into our app and demonstrates the ease of designing layouts using XML in Android development. With everything set up now, let's run your application. Click on the green Play icon in Android Studio. If you haven't yet set up an Android emulator, you can create one by navigating to the AVD Manager, Android Virtual Device Manager, available in the toolbar. Choose your desired device configuration and let the emulator boot up. Once it's up and running, the app should display "Hello, Android" on the screen. Congratulations on setting up your development environment and deploying your first app. So to recap, we've covered the amazing synergy between Android and Java, set up the JDK and Android Studio, and created a simple app that greets users. As you progress deeper into app development, the complexity will rise, but so will the rewards. Keep exploring the features and libraries of Android. You're now equipped with a robust foundation to create amazing applications. Join us in the next tutorial, where we will dive into more advanced features and coding techniques. In the realm of programming, it's almost a rite of passage for newcomers to create their very first application that simply says, "Hello, world." This task might seem trivial, but it serves as a foundational stepping stone into the world of coding, particularly in Android development. In this video, we will take that very first step together by crafting our initial Android app. So far, we learned about setting up the development environment for Android app development, including the importance of Android and its compatibility with Java. We covered the installation of the Java Development Kit, JDK, in Android Studio, and created a simple Hello Android application. Additionally, we explored the basic structure of an Android project and the process of linking Java code with XML layouts. As we continue, we will delve into more advanced features and coding techniques. Before we dive into the code, let's break down what exactly an Android app is. An Android app consists of various components, but the core of your app is its activities. An activity represents a single screen in your app with a user interface. In our case, we're going to create a simple application that has just one activity. This will be our entry point to greet our users with a friendly message. First, let's open Android Studio and get ready to create a new project. When you launch Android Studio, you'll see the welcome screen. Click on Start a new Android Studio project. Choose Empty Activity, as this will give us a clean slate to work with. Now let's name our app. How about Hello World? This name will help represent our app's purpose clearly. You will be prompted to fill in the package name, which typically follows the format of a domain name in reverse order. For instance, if your domain is example.com, you might use example hello world. Next, select the minimum API level. API level 16 Jelly Bean is a good choice, as it supports a wide range of devices. Once you have made these selections, click Finish and watch as Android Studio sets up the project. Now let's implement the onCreate method in our main activity Java, which is essential for initializing our activity. This method is called when the activity is created, serving as the entry point for our UI setup. We start by invoking the super onCreateSavedInstantState method to ensure any necessary operations from the parent class are executed first. This is crucial for the proper functioning of our activity. Next, we utilize the setContentView method to specify the layout file that our activity will use, which in this case is allLayoutActivityMain. This call links our Java code with the XML layout file defined earlier, effectively establishing the visual structure for our user interface. By setting the content view, we ensure that the UI elements we defined in the activity main, XML, are now accessible and displayed on the screen. This creates a bridge between our code logic and the layout design, allowing us to build interactive Android applications. With this method in place, we are well on our way to transforming our app into a working product that greets users effectively. Now let's take a look at how we can define our user interface in the activity main XML file using XML. In this layout, we're employing a linear layout, which serves as a container that arranges its child elements vertically. The attributes set layout width and layout height to match parent, indicating that the layout will expand to fill its parent view both horizontally and vertically, creating a full-screen experience. To center our content, we utilize the gravity attribute, enhancing the visual layout. Inside this linear layout, we'll include a text view to display our greeting. The layout width and layout height attributes of the text view are set to wrap content, ensuring that it adjusts its size based on the content, which in this case is the string Hello Android World. This text is styled with a text size of 24 scale-independent pixels, SB, optimizing readability across various screen sizes. This combination of layout and view components allows for a clean, user-friendly interface that greets users as they launch our application. Thus, we establish a foundational layout that can easily be expanded with further UI elements as we develop more functionalities. Now let's implement a logging statement in our onCreate method to track when the activity is created. This can be incredibly useful for debugging and understanding the flow of your app. By adding the line log_d main activity created, we are instructing the Android framework to log a debug message tagged with main activity whenever this method executes. The log_d method is part of the Android logging system, which provides a way to output messages to the logcat, a tool built into Android Studio that shows logs generated by your app. In this instance, the message activity created will appear in the logcat every time the main activity is initialized. This practice helps developers keep track of critical events during the lifecycle of an activity and can assist in diagnosing issues as they arise. By logging key events, you create a clearer picture of your application's behavior, which is essential when you begin encountering bugs or unexpected behavior. Now it's time to test our first Android app. Click on the green Play button in Android Studio to run the application. If you haven't set up an Android Virtual Device (AVD) yet, don't worry, just go to the AVD Manager from the toolbar and create a new device. Select a device that meets your needs, and once your emulator is running, you will see the Hello Android World message on your screen. Congratulations, you've just developed your very first Android application. Seeing your code come to life is a satisfying experience and an exciting start to your journey in development. Next, let's discuss what happens under the hood. Each time you make a change and build your application, Android Studio compiles your Java code into bytecode that runs on the Dalvik or ART runtime. The XML layouts are compiled likewise. Remember the importance of separating logic from UI. This is where the Model View Controller (MVC) architecture plays an essential role. The activity acts as the controller, handling user interactions and updating the UI, while the XML files, the view, define how the UI should look. As you continue with Android development, you'll find it vital to maintain this separation of concerns. It'll help you write cleaner, more maintainable code, which is especially crucial as your apps become more complex. Now that we have a basic app set up, let's implement user interactivity by creating a button that changes the displayed text when clicked. First, we need to update our layout file, activity main, XML, to include a button component. By adding the button element beneath the existing text view inside the linear layout, the button will be displayed on the screen with the text, "Click me." This simple addition will allow users to interact with our app more dynamically. Next, we will return to main activity Java to set up functionality for this button. At the top of the class, we will declare a variable of type button, which will let us interact with the button in our code. Then inside the onCreate method, we'll use findViewById to obtain a reference to our button based on its ID, which we must first ensure is defined in the XML. To make the button respond when clicked, we will set a click listener that updates the text view's text to button clicked. This allows us to provide immediate feedback to the user, enhancing engagement with our app's interface. In this code snippet, when a user clicks the button, the text in the text view will change to button clicked. This interactivity adds a layer of engagement and dynamism to your app, making it more user-friendly. After modifying the XML for ID declarations and updating the Java code, run your app again on the emulator. You should now see the button on the screen. When you click it, the text will change, confirming that your app responds to user interactions. With this enhancement, you've incorporated essential event handling in your app, which is the foundation of interactive applications. This dynamic behavior is fundamental in user experience design, allowing users to engage with the app meaningfully. At this juncture, let's recap what we've achieved. We started by setting up our environment, explored the project structure, and implemented a simple Hello Android World app. We added a button to handle user clicks, enhancing our app's functionality by changing text dynamically. As you advance in your Android development journey, always keep experimenting with various features. You can explore more UI components like edit text for user inputs, recycle a view for lists, and even integrate APIs for more complex functionality. That brings us to the end of our video. Creating your first Android app is an exciting milestone, and I encourage you to keep pushing your boundaries and learning more. Remember, every great developer started somewhere, and with practice and perseverance, you'll become proficient in no time. Thank you for joining me today, and I hope to see your creativity shine in your next project. Welcome to another exciting tutorial on Android development. Today, we're diving into a crucial topic: building Android applications with Java. We'll explore not just the hows, but also the whys of Android app development, and you'll see just how powerful and fun it can be as we create something awesome together. So far, we have learned about creating our first Android app, starting with the setup of Android Studio and the Java Development Kit, JDK. We built a simple Hello Android World application and explored the structure of an Android project, including the roles of activities and XML layouts. We then added interactivity by implementing a button that changes the displayed text upon being clicked. Lastly, we emphasized the importance of user experience design and encouraged continued exploration of Android development features. Now, we will cover how to enhance our app's functionality by delving deeper into Java programming for Android. Now let's see how we can implement the user interface for our app using XML. We start with a relative layout, which allows us to position child elements relative to each other. The layout's parameters, layout width and layout height, are both set to match parent, meaning it fills the entire screen. Inside this layout, we've defined a text view for displaying our welcome message, Hello Android World. This text view is centered horizontally and has a top margin to create some space from the top of the screen, enhancing its visibility. Below the text, we add a button labeled Click Me. This button also has its dimensions set to wrap its content, ensuring it only takes up as much space as necessary. By positioning it below the text view using the Layout Below attribute, we maintain a clear and organized structure. the use of layout center horizontal centers the button on the screen, creating a balanced layout. This code effectively sets up a simple yet functional interface for our application, making it user-friendly and visually appealing. Next, we will implement the functionality for our button that we created in the XML layout. To achieve this, we begin by overriding the onCreate method, which serves as the entry point for our activity when the app starts. Inside this method, we first call setContentView to connect our activity with the layout we've defined. Now let's take a look at how we work with the button. We create an instance of the button by using the findViewById method, which links the Java code to the button we specified in the XML layout using its ID. This allows us to interact with the button programmatically. Next, we set an onClickListener on our button, which essentially tells the app what to do when the button is clicked. Inside this listener, we override the onClick method, where we define the action that occurs upon a click. In this case, we use a toast to display a brief message, button clicked, to provide immediate feedback to the user. This simple but effective interaction enhances the user experience, making the app feel responsive and engaging. Now let's implement a more organized approach for handling button clicks by defining a custom method. We start by creating a method named onButtonClick, which takes a view parameter and shows a toast message indicating that the button has been clicked. This encapsulation of the toast functionality not only improves the readability of our code, but also adheres to best practices of modularity, making it easier to maintain moving forward. Next, we will modify the button's click listener to use this new method instead of an anonymous inner class. By calling button setOnClickListener, this onButtonClick, we instruct the button to call the onButtonClick method whenever it is clicked. This simplifies the onCreate method and enhances the clarity of our intent. Now it's immediately obvious that clicking the button triggers the action defined in onButtonClick. This approach also allows for easier future modifications. You can expand the method to perform additional tasks, such as updating UI elements or initiating new activities without cluttering the button listener logic, thus promoting a clean and comprehensible code structure. Now let's implement the item class, which will serve as our data model for managing items in our application. This class encapsulates the properties associated with an item, specifically its name. By defining an item class with a private member variable for name and a constructor, we can create instances of this class whenever we need to represent an item. Additionally, the getter method, getName, allows us to retrieve the name of the item when needed, adhering to the principle of encapsulation in object-oriented programming. Next, we'll take a look at how to display these items within a list using a list view. In our XML layout, we add a list view element, specifying its width to match the parent and allowing its height to wrap content. This setup ensures that our list can dynamically adjust to the number of items it contains while maintaining an organized layout. Now let's set up our main activity Java to handle the data. We create an array list to hold our item objects, adding a couple of sample items for demonstration. By utilizing an array adapter, we establish a connection between the list view and the item data, efficiently bridging our data model with the visual representation in the user interface. This setup not only displays the items, but also prepares the app for more complex lists in the future. Next, we will write a line of code that harnesses Android's logging capabilities to monitor user interactions in our app. The statement log d main activity, button clicked, serves as a debugging tool, allowing us to print a debug message to the logcat console. By placing this line inside our button's click event, we can track when the user clicks the button, which is vital for understanding user behavior during runtime. The first parameter, main_activity, acts as a tag that helps categorize the log message, making it easier to filter logs according to different components of your application. The second parameter is the actual message, button clicked, which provides context for the event being logged. This simple yet powerful tool is crucial for diagnosing issues in your app. As your applications become more complex, employing logging statements like this will aid significantly in troubleshooting and ensuring a smoother user experience. In summary, today we've walked through building and improving an Android application with Java. We have enhanced the user interface, added functionality with click listeners, managed data with a custom model, and learned how to utilize debugging tools effectively. As you continue exploring Android development, remember that each small project builds your skills, leading you to create increasingly sophisticated applications. Thank you for joining me today. I hope you found this session informative and definitely not boring. Don't forget to keep experimenting with your code and pushing the limits of what your applications can do. Keep coding, and I'll see you in the next tutorial, where we'll cover even more exciting features in Android Welcome back. Today we will take an exciting guided tour through Android Studio and the project structure that is fundamental to creating Android apps. So far, we've covered the basics of creating our first Android application, exploring layouts, and understanding UI components. In this session, we'll delve deeper into Android Studio's features and help you get comfortable with its environment, which is vital for your development journey. Let's start with a brief overview of what Android Studio is and why it's such a powerful tool for Android development. Android Studio is the official integrated development environment (IDE) for Android app development, built on JetBrains' IntelliJ IDEA. It provides all the essential tools you need to build Android apps, from coding to debugging and deploying your applications. It's crucial to become familiar with its layout and features so that you can work efficiently and effectively on your projects. Before we dive into the details, let's take a moment to reflect on what we've learned thus far. So far, we learned about creating our first Android application, starting with the setup of Android Studio and the Java Development Kit, JDK. We built a simple Hello Android World app, explored UI layouts, and linked user interactions through clickable buttons. We also discussed best practices in organizing code and introduced a custom data model for handling items in a list. Lastly, we learned about debugging tools to improve our application's performance and understand its behavior during runtime. Now, we will cover the main areas of Android Studio, its project structure, and how to navigate through it effectively. First off, as you launch Android Studio, you'll notice the welcome screen. It's the first impression of the development environment and gives you quick access to several important actions, such as starting a new project, opening an existing project, or getting updates about new features. Always take a glance through the tip of the day messages that appear. They can offer valuable insights into features you may find helpful during your projects. Once you start a new project or open an existing one, you're greeted with the main workspace. You'll see various panels and sections working harmoniously to facilitate your development tasks. At the top is the menu bar. This is your command center, where you can find options ranging from creating new files to configuring settings for your project. Let's get familiar with the main components of the interface. The toolbar, located just below the menu bar, offers quick access buttons for common tasks, like running your app or accessing the debugger. If you ever find yourself searching for a specific option, you can rely on these buttons for efficient navigation. Now let's implement the main activity class that serves as the entry point for our Android application. This class extends AppCompatActivity, which is part of the AndroidX library, and provides compatibility with a wide range of Android devices and additional features. Inside the main activity, we override the onCreate method, which is called when the activity is first created. This is where the initialization of our activity occurs. In the onCreate method, the first line calls the superclass's onCreate method, ensuring that any foundational setup performed by the parent class is executed. This is essential as it maintains the integrity of the activity lifecycle. Next, we set the content view using setContentView, linking our activity to a layout resource defined in the activity main, XML file. This layout file describes how the UI will be structured and presented on the screen. By doing so, we establish a direct connection between the code and the visual elements of our app, allowing us to build a user-friendly interface. Through this approach, we lay the groundwork for further development and interaction in our Android application. Now let's take a look at how we can design our app's main interface using XML in the activity main, XML file. This layout uses a linear layout, which is a versatile layout option that organizes its child elements in a vertical or horizontal orientation. In this case, we set its orientation to vertical, ensuring that any views we add will be stacked on top of each other from top to bottom. Inside this linear layout, we have a text view that displays text defined by a string resource. By setting the Android text attribute to @string hello world, we are referring to a string resource that we defined earlier in the strings XML file. This method of utilizing string resources not only keeps our code cleaner, but it also aids in localization, allowing us to easily adapt our app for different languages in the future. Next, we define both the width and height of the text view as wrap content, allowing it to adjust dynamically to the text size, thus ensuring a responsive design. Overall, this XML structure builds a foundational layout for our application, setting the stage for further enhancements and interactions as we move forward in the development process. Now let's take a look at how to define string resources in Android. In the strings XML file, we encapsulate our text resources within XML tags, starting with resources. This is a foundational file that enables us to manage all the text displayed in our application, promoting a clean separation of code and layout. Within this structure, we define individual string resources using the string tag, specifying a unique name for each string through the name attribute. For instance, we've created a string resource named appName with the value myFirstApp, which serves as the title of our application, and another resource called Hello World that holds the text Hello Android World. By utilizing these string resources, we can easily reference them throughout our application using the @string syntax. This method not only improves code readability, but also simplifies the localization process, allowing for seamless translations if we decide to make our app available in multiple languages. Now let's see how we can implement this by referencing @string hello world within our layout XML files, ensuring a consistent user experience across different screens. Now let's pivot to the editor itself, which is the heart of your coding experience in Android Studio. Depending on what file type you've opened, a Java file or an XML layout, the editor will dynamically transform, displaying the relevant UI for that type. This dynamic nature helps streamline the development process, allowing you to focus on the task at hand without getting bogged down with unnecessary details. For instance, when you open an XML layout file, you'll have access to a visual design tool alongside the code editor. Any UI element you add via the palette will automatically reflect in the XML code. The palette contains various components and widgets that you can drag and drop onto your layout. Let's talk about how to effectively use the palette. Now let's take a look at how we can implement a button in our XML layout. The code snippet shows a button element, which is a fundamental UI component in Android applications, allowing users to perform actions when tapped. In this example, we specify two important properties: Android layout width and Android layout height. Both are set to wrap content, which means the button will adjust its size to fit the content within it, ensuring it only takes up as much space as necessary. This is particularly useful for user interfaces where space is limited or when you want a dynamic layout that adapts based on user interactions or content changes. The Android text attribute is where we define the label displayed on the button itself. Here, it's set to "Click Me," a clear invitation for users to interact. This text will be easily visible to users, making it known that a click will trigger some action. When you integrate this button into your layout using the drag-and-drop feature from the palette in Android Studio, you'll see how the visual representation aligns with this XML code. This process not only simplifies development, but also helps maintain a clean structure, allowing for more efficient UI management. Lastly, as we wrap up our exploration, let's not forget the debugging tools available within Android Studio. The console and logcat windows are crucial for monitoring your app's performance. Any errors or system messages generated as your app runs can be viewed here, which aids in debugging. Always keep an eye on the event log for any updates or important information regarding your builds. In conclusion, Android Studio is more than just an IDE. It's a comprehensive development environment equipped to handle everything from coding to debugging and resource management. By understanding its layout, learning to navigate through the project structure, and effectively using the features at your disposal, you're setting yourself up for success in your Android development journey. So there you have it, your guided tour of Android Studio and the essential project structure. We've covered everything from the menu bar to layout designs and debugging. I hope you're feeling a whole lot more confident with this tool now. Join me in the next session, where we will start diving deeper into UI design and begin creating some significant real-world layouts for our application. Let's dive into designing layouts in Android. Understanding how to control the size, position, and appearance of widgets is key to creating intuitive and beautiful interfaces. So far, we learned about the basics of Android Studio and created our first application. Now, we will explore various UI fundamentals, including how to position widgets precisely and manipulate XML layout code to achieve the desired design. Now let's take a look at a simple layout structure that serves as a foundation for creating an Android interface. In this code, we start with a relative layout, which allows us to position elements in relation to each other. The XMLNS Android attribute defines the XML namespace and is required for Android layouts. We set the layout width and height to match parent, ensuring the layout fills the entire screen. Inside this relative layout, we have a text view that displays Hello World. This widget's width and height are set to wrap content, allowing it to expand just enough to fit the text. The simplicity of this layout enables a clear starting point for beginners, helping to understand how layout components interact. Next, we will write the following code to add another text view beneath the first. By using the Layout Below attribute, we can specify that this new text view should be positioned directly below the first text view with the ID text view. This capability of relative layout makes it easier to manage widget positioning without nesting multiple layouts, thus creating an intuitive UI design. Now let's implement the following attributes to specify the size of a view in our layout. In Android, we often use density-independent pixels, or DP, which ensures that our layouts appear consistent across various devices. By setting Android width equals 150 dp and Android height equals 50 dp, we define the exact dimensions of a view, allowing it to adapt to different screen densities while maintaining the intended appearance. This guarantees that regardless of whether the app runs on a phone or tablet, the sizing will feel harmonious. Next, we will examine how to configure the text size within our views. Android utilizes scale-independent pixels, or SB, to define text size, ensuring that it respects users' font size preferences set in their device settings. By using Android text size equals 16 SB, we establish a legible font size that remains accessible and adjustable for users who may require larger or smaller text. This consideration promotes inclusivity in your app's design, making sure that all users have a pleasant reading experience. Through these attributes, we enhance the accessibility and usability of our app while ensuring it looks great on any device. Now let's examine how to effectively implement margins in your layouts with a button. When adding a button, you might want it to have equal spacing around it to ensure it stands out effectively within your interface. By setting Android layout margin equals 20 dp, we define a uniform margin of 20 density-independent pixels on all sides of the button. This added space ensures that the button doesn't feel cramped against other elements, enhancing the visual appearance of your layout. Next, we can look at another approach to margin customization that offers more control over each side individually. By specifying Android layout margin top, Android layout margin bottom, Android layout margin left, and Android layout margin right, you can fine-tune the button's positioning. This means you can give more space above or below the button while adjusting the left and right margins as needed. Such customization can be particularly useful for creating responsive designs that adapt well to different screen sizes and orientations, ensuring your layout remains intuitive and organized. Now let's explore how to create a vertical layout using linear layout ***. In this example, we define a linear layout with its width and height set to match the parent container, ensuring that it occupies the full available screen space. By setting the orientation attribute to vertical, we instruct the layout to stack its child elements, which in this case are two buttons, one below the other. Next, we will add our buttons within this layout. Each button is given a width and height of wrap content, meaning they'll adjust their size based on the text they contain. The first button is labeled First Button, while the second one is Second Button. This simple arrangement demonstrates how linear layout can efficiently stack components in a straightforward manner. Now let's take a look at how we can enhance this layout using layout weight for greater flexibility during device scaling. Each button can have a layout weight assigned, which controls how space is distributed among them. For instance, setting the layout weight of the first button to 1 and the second button to 2 ensures that the second button will occupy twice the space of the first, allowing for a responsive design suitable for different screen sizes and orientations. Now let's take a look at how we can align content within widgets using properties like ***, gravity ***, and layout gravity ***. In the first code snippet, we define a button with the gravity property set to center. This means that any text displayed within the button will be centered both vertically and horizontally, providing a clean and polished appearance. Such alignment is crucial for enhancing user interaction and making the UI visually appealing. Next, we will implement the layout gravity property in our button. In the second code snippet, the button is positioned to the right of its parent layout. While gravity controls the alignment of the content inside the widget, layout gravity determines how the widget itself is positioned within its parent container. This distinction allows us to create more dynamic layouts that take full advantage of the available screen space. By mastering these properties, you can ensure that your UI elements are both functional and aesthetically pleasing, contributing to a seamless user experience. Now let's implement the following code to see how we can use the relative layout more effectively. This layout allows us to position widgets in relation to one another, providing significant flexibility in our design. In this example, we create a relative layout that fills the available space on the screen. Within this layout, we add a text view at the top, which serves as a label for our interface. It displays the text "I'm at the top" and is defined with parameters that allow it to wrap its content, ensuring it only takes up the space it needs. The crucial part here is the padding and sizing, as it allows other elements underneath to be properly aligned. Next, we include a button below this text view. By utilizing the Layout Below attribute, we specify that this button should appear directly underneath the text view, creating a clear relationship between the two. This direct referencing through IDs simplifies positioning and enhances our ability to maintain a coherent layout without unnecessary nesting, ultimately supporting a cleaner and more efficient user interface. With these insights into layout design in Android, you're well on your way to becoming a pro UI designer. Remember, practice is essential. The more layouts you create, the better you'll understand how to manipulate them. Don't hesitate to experiment, adjust properties, and see how changes reflect in real time. As you continue building interfaces, you'll discover which layouts are most suited for your particular needs. Embrace the complexity and let your creativity guide you. In summary, today we've extensively covered the fundamentals of designing layouts in Android, focusing on widget positioning, sizing, and the various layout types available. Remember to apply what you've learned as you proceed to create your own unique app interfaces. With each design, you're inching closer to crafting visually stunning and user-friendly applications. Creating real-world user interfaces in Android is an engaging journey into making apps not just functional, but visually appealing and user-friendly. Today, we will dive into a hands-on approach, creating practical UI designs that might very well end up in an actual application. So far, we learned the fundamentals of designing layouts in Android, focusing on controlling sizes, positions, and appearances of widgets to create intuitive interfaces. We explored the basics of XML layout definitions and various layout types, such as linear layout and relative layout, to manipulate UI elements efficiently. We also discussed using density-independent pixels for sizing and the significance of margins and padding in creating appealing layouts. Finally, we emphasized the importance of practice and experimentation in mastering layout design as you build more user-friendly applications. Now, we will talk about how to build real-world user interfaces in Android, diving into projects that push our understanding further. Now let's take a look at how to structure our list detail layout in XML. The first step involves creating a horizontal linear layout that serves as the root of our layout. This layout will hold two child linear layouts, one for displaying the list of items and the other for showcasing the details of the selected item. The primary linear layout is set to match the parent for both width and height, ensuring it occupies the entire available screen space. Next, we will implement the two child linear layouts. The first one, designated for the list, is assigned an ID, a width of 0 dp, height as match parent, and a layout weight of 0.4, which specifies that it should take 40% of the available width. In contrast, the second linear layout is dedicated to the detail view, also with an ID and a weight of 0.6, thus utilizing the remaining 60% of the horizontal space. This division allows for an intuitive layout where users can easily navigate between the list of items and their corresponding details, creating a smooth user experience akin to many applications. Now let's implement the following code to set up our list and dynamically populate it with items. Within the onCreate method of main activity, we call setContentView our layout, list detail layout, to set the layout we just created, which includes our list. Next, we need to locate the linear layout that will hold our list items by referencing it through its ID, our ID in a list layout. We will then use a loop to create and add 20 text view elements, each displaying item 1, item 2, and so forth. By doing this, we are dynamically creating UI elements at runtime, which allows the user to interact with a functional list. As we create each text view, we also set it to the corresponding item text and add it to the inner list layout. This ensures that as we run our app, users will see a scrollable list with neatly organized items that they can scroll through. This approach emphasizes how we can construct user interfaces programmatically, providing a more dynamic and responsive application experience. Next, we will implement the listener for our list items, which is crucial for updating the detail section based on the user's selection. Here, we set an on-click listener for each text view representing a list item. When a user clicks on an item, this listener triggers and allows us to perform an action in response to that interaction. Inside the listener, we first locate the text view in our detail layout by its ID. Once we have access to this text view, we can dynamically change its text to display relevant information. Specifically, we update it by concatenating the string details about with the text of the clicked item. This creates a responsive detail view that seamlessly changes according to user input, enhancing the overall user experience in our interface. Now let's also ensure that the layout for the detail section is properly structured. We define a linear layout to house the detailed text view, setting its dimensions to match the parent, and using a weight to distribute space effectively. As a result, when the user taps on different items in the list, they see immediate updates in the detail layout, allowing for a cohesive and interactive application design. Now let's proceed to build the form layout for user input. The first step involves creating a linear layout in our form layout, XML, which serves as the container for all the form fields. This layout is set to match the parent's width and height while having a vertical orientation, ensuring that all child views stack vertically, providing a clean and organized appearance. Next, we will add several edit text fields to capture user information such as name, email, password, and confirm password. Each edit text is assigned a unique ID, allowing us to reference them later in our Java code. The hints provided in each field guide the user on what information to input. Now let's implement a button below the last edit text field. This button, when clicked, will trigger logic to collect the user-entered data. We will set up an on-click listener that, upon clicking the button, retrieves the text from the edit text fields and displays a welcome message along with the user's email using a toast. This interactive feedback will enhance the user experience by confirming successful input. Each of these components works together to create an intuitive and interactive form for users to fill out. Now let's implement the button that will handle form submission. We begin by declaring a button variable and linking it to our XML layout using its ID, which we assigned as button submit. This establishes a connection between our Java code and the button in the user interface. Next, we assign an on-click listener to the button, allowing us to specify what happens when the user clicks it. Inside the onClick method of the listener, we will retrieve the text inputted by the user from the various edit text fields we previously defined. These fields include the user's name, email, password, and confirm password, each accessible by their unique IDs. This is essential for gathering user data on submission. To provide immediate feedback, we create a message string that welcomes the user by name and confirms their email address. This message is then displayed using a toast, a small pop-up notification that appears briefly on the screen. This confirms a successful submission, enhancing user interaction. Don't forget to import the toast class at the beginning of your code to ensure everything runs smoothly. As we step back and look at our two projects, a list detail layout and a simple form submission layout, what do we see? We see that building user interfaces in Android is not just about creating pretty screens. It's about creating experiences, ensuring users can navigate intuitively while engaging with our applications. These designs we created might seem basic, but they embody the principles upon which we can craft more complex applications. They illustrate clear, organized layouts, allow users to interact easily, and provide immediate feedback. Remember, as we continue our journey into Android development, the practice and experimentation are critical to mastering user interface design. Each project, big or small, is a stepping stone toward consuming a full-fledged application. So get coding, break things, and most importantly, have fun while building your applications. Thanks for watching, and I hope to see you in the next lesson. Understanding the Android application lifecycle management is essential for every developer looking to create robust applications. In today's discussion, we will explore the various states an Android application can go through during its lifecycle, including the methods that the system calls during these transitions. So far, we covered the fundamentals of creating user-friendly interfaces in Android, focusing on designing layouts with XML and various layout types. We explored developing a list detail layout, where selecting an item reveals more details, and a form submission layout for capturing user input. We emphasized the importance of interaction and user feedback in interface design, along with the need for practice and experimentation. Moving forward, we will delve into Android's application lifecycle management, which is crucial for optimizing the performance of your apps. Now let's take a look at how we can implement the key lifecycle methods in our Android activity to manage application states effectively. The onCreate method is the first callback that the system invokes, where we typically initialize our activity. Here, we set the content view for our activity and log a message indicating that this method has been called. Next, we implement the onStart method, which is called when the activity is becoming visible to the user. This is an excellent place to initialize any resources needed while the app is still visible. After that, the onResume method is triggered when the activity comes to the foreground, allowing us to focus on tasks that require user interaction, such as starting animations or refreshing data. When the user navigates away from the app, the onPause method is invoked. Here we can pause ongoing tasks, save data, or release resources, ensuring that our application behaves gracefully during interruptions. Similarly, onStop is called when the activity is no longer visible. We can use this time to clean up resources that are not needed when the app is in the background. Lastly, the onDestroy method allows for final cleanups before the activity is destroyed, providing a last opportunity to release any remaining resources. This systematic approach ensures a smooth user experience throughout the application's lifecycle. Now let's see how we can implement lifecycle management with a focus on saving and restoring user data efficiently. The onPause method is designed to handle tasks when the application moves to the background. Here, we call save user data to secure any input from the user, ensuring that important information is not lost. Additionally, we invoke stop data sync to halt any ongoing data synchronization activities, which helps conserve bandwidth and resources during this transitional state. Next, when the user returns to the app, the onResume method is triggered. This is where we load the previously saved user data using load user data, so that users see their prior inputs without any disruption. We also restart data synchronization by calling start data sync, re-establishing network connections necessary for background updates. This careful management of data and network resources is especially crucial in mobile development, where both device limitations and user expectations necessitate a seamless experience. Implementing these methods enhances the overall functionality of the app, ensuring users can navigate fluidly without losing their context or data. Next, we will write a code snippet that showcases how to manage resources effectively when an application goes into the stopped and destroyed states. In the onStop method, we begin by invoking the superclass method and then log a message indicating that the application is cleaning up resources. This is a critical moment for the app, allowing us to release resources that are no longer needed, which could include closing database connections or clearing cached data. Following this, we proceed to the onDestroy method, where we again call the superclass method to ensure proper handling of the lifecycle. Here, we log a message that signifies finalizing resources before the app closes completely. This method acts as a safeguard to check that everything is in order before the application is entirely freed from memory. Additionally, we implement two helper methods, cleanup resources and finalize resources. The former is tasked with managing resource cleanup during the stop state, while the latter ensures that any remaining tasks are completed correctly in preparation for the app's destruction. Utilizing these methods enhances the app's reliability and prepares it better for resumes after being stopped. Now let's implement the following methods to manage configuration changes effectively within the activity lifecycle. We start with the onSaveInstance method, which is crucial for preserving the activity's state before it is destroyed during events like device rotation. This method is called before the activity is recreated, allowing us to save any essential data, such as UI state, in the provided bundle object. In our example, we simply log a message to indicate that saving is in progress and put a sample key value pair into the outState bundle. Next, we'll look at onRestoreInstance, which comes into play when the activity is recreated after being destroyed. This method allows us to retrieve the saved state from the bundle that we populated earlier. By leveraging this method, we can restore any lost data and maintain the continuity of the user experience. Here, we also log the restoration process and extract the value associated with our key, ensuring that even after a configuration change, the app's interface and data feel consistent to the user. This practice is indispensable for creating robust Android applications that handle lifecycle events gracefully. Now let's implement the code for a background service that runs independently of the UI thread. The provided code defines a class called myService, which extends the service class, allowing it to run in the background. The onStart command method is the entry point that Android calls to start the service. Here, we log a message to indicate that the service has started, which is useful for debugging and monitoring service activity. The comment within this method suggests where to perform background tasks, making it clear that any intended ongoing operations should be implemented within this method to avoid disrupting the user experience. The return value of startSticky instructs the system to recreate the service if it is killed, which is beneficial for tasks that need to run continuously. This approach supports cases where the service can continue running even when the app's UI is not visible. Next, we have the onDestroy method, which is invoked when the service is no longer needed. Here, we perform cleanup tasks, including releasing any resources or connections. The log statement here is equally important as it helps track the service's lifecycle events. By managing a service correctly in this way, we ensure our application can handle background processing efficiently while maintaining a smooth user experience. Now let's take a look at how we can efficiently manage user data and application state during various lifecycle events. In our code, we override several key lifecycle methods: onPause, onResume, onStop, and onDestroy. The onPause method is used to save any user data by invoking the SaveUserData method, ensuring that persistent data like the username is stored securely, likely using shared preferences for simplicity. Simultaneously, we stop any data synchronization processes to conserve resources while the app is not in the foreground. In the onResume method, we load the previously saved user data and restart any data synchronization that was paused, ensuring that the user's experience remains seamless when they return to the app. Moving on to onStop, this method is responsible for cleaning up resources that are no longer needed, which helps to manage memory and prevent resource leaks. Finally, onDestroy is called when the activity is finishing, which allows us to finalize any remaining resources, ensuring a clean exit from the application. By neatly organizing these methods, we maintain a responsive and user-friendly application, effectively handling state changes and user data throughout the app's lifecycle. In this lesson, we have explored the intricate workings of Android application lifecycle management. We covered the application states, the importance of lifecycle methods, resource management, configuration changes, and how to handle background processes effectively. Keeping your app efficient during state transitions and managing data correctly are key factors in developing high-quality Android applications. As you continue your journey in Android development, practice implementing these concepts to ensure that your applications remain user-focused and The core fundamentals of Java are essential for your journey into Android development. Understanding how these concepts work is crucial for creating robust, efficient, and scalable Android applications. In this session, we will dive deep into variables, data types, control structures, and methods, all fundamental to any programming endeavor, especially in Java for Android. So far, we learned about Android application lifecycle management, highlighting its various states: active, paused, stopped, and destroyed. We explored key lifecycle methods and discussed the importance of managing resources, user data, and background tasks for a seamless user experience. Additionally, we addressed handling configuration changes and ensuring data persistence during transitions. Properly implementing these concepts is vital for delivering a polished and responsive application. Now we will talk about the core fundamentals of Java, focusing on code that goes into classes, methods that we create, and the data that the code acts upon. Now let's see how we can define a variable in Java, which is crucial for tracking information throughout our program. In this example, we declare an integer variable named unreadMessages and initialize it to 0. This means that when our application starts, it will consider the starting point for unreadMessages as 0. Defining variables like this allows us to store data that can be manipulated and referenced later in the program. It's important to note that Java is a case-sensitive language. Therefore, using unreadMessages is different from unreadMessages. This distinction reminds us to be consistent with our variable naming conventions to prevent confusion. In the context of Android development, being mindful of variable age ensures that we effectively manage user data and application state, both vital for providing a smooth user experience. Variables serve as the building blocks for more complex structures, reinforcing the importance of a strong foundational understanding in Java programming. Now let's take a look at how we can declare different types of variables in Java, which is essential for managing data effectively in our application. We start with an int for unreadMessages, initializing it to 0, which serves as a counter for the number of messages that users have yet to read. Next, we introduce a float type for account balance, where we store financial figures with decimal precision, ensuring we maintain accuracy in our calculations. The Boolean type for isNewUser simply indicates whether the user is new or returning, a crucial variable for determining the user experience. In addition, we utilize a char for first initial, allowing us to capture a single character, which could represent a user's first initial in a more compact form. Finally, we define username as a string, accommodating the user's name, which may contain multiple characters. By understanding how to effectively assign data types to variables, we enhance our program's capability to manage different kinds of data efficiently, paving the way for more complex operations as we continue our exploration in Java development. Now let's see how we can implement the concept of variable manipulation using arithmetic operations. In our example, we start by defining two integer variables, total messages, initialized with the value of 5, and new messages, set to 3. These variables represent the number of messages that are currently in different states. Next, we create a third variable called allMessages, which adds the values of the total messages and new messages together. This operation exemplifies how we can combine different variables to derive a new value, demonstrating the foundational principle of arithmetic manipulation in programming. Additionally, we can make use of incrementing and decrementing operations to adjust the values of our variables. By utilizing the ++ operator, we can easily increase total messages by 1, thus updating our data to reflect any new message received. On the other hand, the operator allows us to decrease new messages by 1, effectively managing the count of incoming notifications. These increment and decrement operations are particularly useful for maintaining counters in applications, enhancing the dynamic nature of our Java programs. Now let's take a look at how we can manage user notifications using conditional statements in Java. Here, we have an if statement that evaluates whether the variable unread messages is greater than 0. This condition checks if the user has any unread messages. If the condition is true, the program logs a message indicating that the user has unread messages. On the other hand, if the condition is false, the else block executes, logging an alternative message that informs the user there are no new messages. This structure ensures that the program responds appropriately to different states of the unread messages variable, enhancing user experience by providing relevant notifications based on their situation. Next, we will implement a simple for loop to demonstrate how we can use iteration in our Java code. In this example, the loop initializes a counter variable, I, to 0 and continues incrementing it until it reaches 5. Each cycle of the loop logs the current value of I, showcasing a counting mechanism. This demonstrates not only how to perform repetitive tasks in Java, but also how loops can assist in executing code blocks multiple times efficiently, which is characteristic of many programming scenarios. Now let's take a look at how nested loops function in Java, providing us with a powerful tool for handling complex iterations. In this snippet, we start with an outer loop controlled by the variable I, which iterates from 0 to 2. Inside this outer loop, we nest another loop that operates with the variable j, running from 0 to 1. This structure allows us to generate a combination of outputs for both loops. For each cycle of the outer loop, the inner loop completes all its iterations, effectively letting us see the relationship between the two indexing variables. The use of the logging statement illustrates which specific iteration of the outer loop is currently executing alongside the running of the inner loop. This is particularly beneficial in scenarios such as managing two-dimensional arrays or generating combinations of elements, where understanding the progression of both loops is essential. By observing the results, you'll understand how nested loops can be applied to various programming challenges, enhancing your ability to handle iterations in a structured and visually informative manner. Now let's take a look at how to implement a simple method in Java for displaying messages in an Android application. In the code, we define a method called showMessage, which takes a string parameter named message. This method utilizes the Toast class, a part of the Android framework that provides a simple way to display short messages to users. The essential feature of this method is its ability to show the message briefly on the screen, enhancing user interaction. When we call toastMakeText, we pass 3 parameters. The current context, this refers to the current instance of the activity, the message we want to display, and the duration for which the toast should be visible, in this case toast, length short, indicating it will display for a short period. By wrapping this functionality within a method, we promote modularity and reusability, allowing us to call showMessage wherever needed in our application without rewriting the display logic. This encapsulation of functionality not only improves clarity, but also aligns with best practices for efficient code organization in Java and Android development. Now let's take a look at a simple Java class that encapsulates both data and behavior, illustrating the principles of object-oriented programming in Java. In this example, we define a class named user that captures user-specific attributes and actions. The class has 2 private attributes: name, which is a string representing the user's name, and unread messages, an integer indicating the count of messages the user has not yet viewed. Next, we implement a constructor for the user class, which is a special method invoked when an object of this class is created. This constructor initializes the name attribute with the value provided when creating a new user instance, and it sets unread messages to 0, indicating that the user starts with no unread messages. Additionally, we define a method called greet, which when called will log a friendly greeting message to the console, including the user's name. This method demonstrates how we can define behaviors that are associated with the user object. By using classes in this way, we not only manage data, but also encapsulate related functionality, enabling cleaner, more organized code in our applications. As you delve deeper into Java programming, it's important to practice these concepts regularly. The more you experiment with variables, control structures, methods, and classes, the easier they will become to use. Remember, coding is as much about logic as it is about creativity. Enjoy the journey and don't hesitate to reach out whenever you run into bumps. That's how we learn and grow. By mastering these fundamentals of Java, you'll lay a solid foundation that prepares you for more advanced topics, such as object-oriented programming and Android-specific frameworks. The sky's the limit once you grasp these. So what exactly are Java methods? A method is a collection of variables, expressions, and control flow statements bundled together inside an opening curly brace and closing curly brace preceded by a name. As we continue on our journey through Java programming, we'll dive deeper into methods because they are not only integral to writing effective code, but are crucial for building robust applications. So far, we've learned about the core fundamentals of Java, focusing on its syntax, variables, data types, control structures, and methods themselves. Now, we will cover the structure of methods, how they work, and some advanced topics like overloading and returning values. Now, let's take a look at a practical example of methods in action within an Android application. Here, we have a class called MainActivity, which is the entry point for the app. Inside the onCreate method, we set up the user interface and perform some initial calculations. This method is crucial as it is invoked when the activity is created. We define two specific methods, calculate circle area and calculate rectangle area. The first method takes a radius parameter and computes the area of a circle using the formula pi2. The use of math pi to get the value of pi showcases Java's built-in functionality for mathematical operations. In the second method, we calculate the area of a rectangle by multiplying the length and width parameters. These methods encapsulate the logic for calculating areas, helping to keep our code organized and reusable. By calling these methods within onCreate, we separate the calculation logic from the UI setup, making the overall design cleaner and easier to maintain. This approach also enhances the readability of the code, emphasizing the purpose of each section within the activity's lifecycle. Next, we will explore how to call a method in Java and handle its return value. In the code, we invoke the sum method by passing the arguments 5 and 3. This call effectively sends these values into the method, where they are assigned to the parameters a and b respectively. The method then processes these inputs by adding them together, resulting in the value 8. Once the addition is performed, the method returns this result back to the caller. The return value is then stored in a variable named result. This step is a clear demonstration of how methods can produce output that can be utilized later in the program, allowing for organized and reusable code. It's important to recognize that after the method execution is complete, control is automatically returned to the point right after the method call, meaning the program continues running smoothly from that point onward. This flow of execution is a fundamental aspect of how methods enhance code structure and readability, making Java programming more efficient and manageable. Now let's take a look at a method that checks if a number is even, a simple yet effective example to demonstrate return types in Java. Here, we define a method named isEven that takes an integer parameter called number. Within this method, we use the modulo operator to determine if the number is divisible by 2. If it is, the method returns true, indicating the number is even. Otherwise, it returns false. This clarity and functionality showcases how methods can encapsulate logic, making our code reusable and maintainable. Next, we will see how we can call this method by passing the integer value 4 to it. Upon invoking isEven4, it evaluates whether the number is even. The outcome true in this case is assigned to the variable is4even. This illustrates the practical use of return types, as the method provides valuable information that can be utilized elsewhere in the application. Understanding this concept is fundamental for implementing logic in Java, such as conditionals or calculations based on method outputs in your applications. Now let's take a look at an example of a method that utilizes parameters to generate a personalized greeting. In this case, we define a method named greetUser, which takes a single parameter of type string called name. This method concatenates the string hello with the value of name followed by an exclamation mark, effectively creating a greeting message that incorporates the user's name. This showcases how methods can dynamically respond to input, allowing for a more personalized experience. Next, we'll see how we can invoke this method in practice. By calling greetUser with the argument Alice, we can store the result in a variable named greeting. As a result, greeting will contain the string hello Alice. This illustrates not only the functionality of method parameters, but also the concept of returning values. The ability to pass data into methods and receive personalized outputs enhances the flexibility of our code, allowing us to build more interactive and user-friendly applications. The clear structure and definition of the method also promote better code organization and readability, which are essential aspects of effective programming practices. Now let's take a look at a method that demonstrates the concept of passing values in Java. we have a simple method named changeValue, which accepts an integer parameter named a. Inside the method, we increment a by 1. This is a straightforward operation, but it serves to illustrate an important concept in Java, the notion of passing parameters by value. When we call the changeValue method and provide it with an integer, say 5, we might expect the original value of a to change outside the method as well. However, this is not the case. After executing the method, when we return to the calling context, the value of a remains 5. This happens because the method works with a copy of the original value. The original variable remains unaffected, showcasing the principle of variable scope within methods. Understanding how Java deals with method parameters and the concept of passing by value is crucial, as it helps prevent unintended side effects in your code, allowing for more predictable and maintainable programs. Next, let's see how we can implement method overloading in Java. We have two display methods defined, one that accepts an integer parameter and another that takes a string. This example illustrates how we can perform similar actions, displaying information to the console, while allowing for different types of input. When we call display10, this invokes the first method which processes the integer and prints it as number 10. Conversely, when we call display hello, it triggers the second method tailored for string input, which outputs text hello. Java intelligently determines which method to execute based on the argument type provided at the call site. This flexibility in method invocation not only improves code readability, but also enhances maintainability, as you can define additional display methods with different parameter types as needed. Understanding method overloading is crucial for writing efficient and organized Java applications, especially as you work with more complex functionalities later in your programming journey. Now let's take a look at how we can implement method overriding in our Java application. In this code, we define a base class called animal, which has a method named makeSound. This method outputs a default message indicating that an animal makes a sound. By itself, this class lays the groundwork for creating different types of animals, each with its specific sound. Next, we create a subclass called dog that extends the animal class. This is where method overriding comes into play. The dog class provides its implementation of the makeSound method, which overrides the behavior defined in animal. Specifically, when an instance of dog calls makeSound, it displays dog barks. This demonstrates how subclasses can tailor their functionality to meet specific requirements while still maintaining a relationship with the superclass. This feature allows us to write code that's cleaner and relies on polymorphism, where the program can call the overridden method without knowing the specific class type. Consequently, using method overriding helps maintain a consistent interface while still providing flexibility in behavior based on the specific subclass. Now let's implement a small Android application that calculates the area of different shapes. In our main activity, we begin by overriding the onCreate method, which is crucial for initializing our activity. Here, we set the user interface layout using setContentView, linking to a predefined XML layout. Next, we will create methods to handle the calculations: calculate circle area and calculate rectangle area. The calculate circle area method takes a radius as a parameter and utilizes the mathematical formula for the area of a circle, pi radius, in order to return the computed area. This clear separation of functionality helps maintain clean code, ensuring that the primary logic in onCreate remains straightforward and easy to follow. Similarly, the calculate rectangle area method accepts two parameters, the length and width, and applies the simple area formula for rectangles, which simply multiplies these two values together. Both results are then logged for analysis, giving immediate feedback on the calculated areas of the shapes when the application runs. This structure not only encapsulates functionality effectively, but also reinforces the Java principle of modular code design. In conclusion, methods are essentially the building blocks of Java programming. They encapsulate functionality, improving code organization and reusability. Understanding how to define, call, and manipulate methods will empower you to write clearer and more efficient code. Remember, so far we covered the fundamentals of Java, including methods, structure, parameters, return types, and concepts like method overloading and overriding. Now, armed with this knowledge, you can elevate your Java programming skills into the realm of creating advanced, functional applications. Now let's take a look at how we can implement a bank account class to demonstrate encapsulation. The bank account class contains a private variable balance, which is safeguarded from external access. This shielding ensures that only methods within the class can modify the balance, promoting data integrity. We initialize the balance through a constructor that accepts an initial value. This constructor sets the balance at the time of the bank account's creation. Next, we provide public methods for users to interact with their accounts: deposit, withdraw, and get balance. The deposit method allows users to increase their balance, but only if the deposit amount is positive, while the withdraw method checks to ensure that withdrawals do not exceed the available balance, preventing errors such as overdrawing the account. Lastly, the get balance method offers a way to access the current balance safely. By restricting direct access to the balance variable and allowing only controlled interactions through these public methods, we maintain a strong encapsulation framework that minimizes the risk of unintended modifications and enhances the overall security of the banking application. Now let's take a look at how we can enhance our bank account class by adding a transaction history feature that logs every deposit and withdrawal. In this implementation, we introduced a private ArrayList string called transaction history to store records of each transaction. This logs the details of the amounts deposited or withdrawn, ensuring we keep track of every financial operation. When we initialize a bank account instance, we set up both the initial balance and instantiate the transaction history list. The deposit method has been modified to log a transaction when a deposit occurs, capturing the amount deposited with a descriptive message. Similarly, the withdraw method will log a transaction when funds are withdrawn, provided the withdrawal is valid. By exposing a public method, getTransactionHistory, we allow external users to retrieve the transaction log without granting direct access to the transaction history variable. This adherence to encapsulation means users can still perform necessary actions on the bank account while ensuring that the internal workings of the transaction history are hidden, thereby maintaining integrity and reducing complexity in our code management. Next, we will implement a security feature in our bank account class to manage user authentication effectively. This involves adding a private Boolean variable, isAuthenticated, which tracks whether a user is logged in. The constructor initializes the account with a starting balance, and we have a method called AuthenticateUser, which simulates the authentication process by setting isAuthenticated to true. Now let's see how we can safeguard the core functionalities of our class. The deposit, withdraw, and get balance methods include checks to verify if the user is authenticated before allowing any operations. If a user tries to perform an action without being authenticated, a message is printed, indicating that access has been denied. This ensures that sensitive operations like depositing or withdrawing funds, as well as checking the account balance, are protected from unauthorized access, reinforcing the concept of encapsulation. By implementing these restrictions, we enhance the security of our banking application, making sure that operations are only performed by verified users, thus maintaining the integrity of the account data. This feature is essential, especially when handling sensitive information such as financial transactions. Now let's take a look at the customer class, which represents a customer interacting with their bank account. This class establishes an encapsulated relationship with the bank account class, meaning it focuses on the customer's actions while hiding the complexities of the banking operations. The customer class starts with two private attributes: name, representing the customer's name, and account, an instance of the bank account class that holds the customer's financial records. The constructor initializes these attributes, creating a new bank account with an initial balance set by the user. Next, we see how the customer class provides methods for depositing and withdrawing money. By having public methods like deposit to account and withdraw from account, the customer class enables users to interact with their accounts without exposing the inner workings of the bank account. This aligns with the principles of encapsulation, as it allows control and validation of these actions internally. Finally, the check balance method is provided to allow customers to view their current balance, further demonstrating the clear and direct interface that encapsulation promotes. This design not only enhances security by hiding account details, but also simplifies interactions, making the code easier to maintain and understand. To summarize what we have covered so far, we have dived into the essential concept of encapsulation in object-oriented programming. We discussed how encapsulation helps in maintaining data integrity and security while promoting flexibility and easier maintenance. We explored the potential of method regulations to safeguard our data through controlled access, preventing accidental modifications. We also looked at how encapsulation fosters the development of cohesive, low-coupling software designs, demonstrating this through the bank account and customer classes, which support pragmatic examples of real-world applications. Now, looking forward, we will introduce the second key principle of object-oriented programming: inheritance. Inheritance allows one class to inherit the properties and behaviors of another, and it facilitates code reuse and the establishment of hierarchical relationships in your codebase, which we will explore in detail next. Take a moment to digest encapsulation, as mastering its principles will lay a strong foundation for understanding inheritance and polymorphism, the remaining pillars of object-oriented programming. Remember, like a treasure chest, encapsulation keeps your data safe, ready for you to explore opportunities for understanding Android UI elements as classes can significantly enhance your app development process, providing the framework for creating interactive user interfaces. Each UI element in Android, from buttons to text fields, is represented as a class in Java. By mastering this connection, you will unlock the potential to enrich your applications with dynamic and responsive elements. So far, we learned about the principle of encapsulation in object-oriented programming, which helps protect the internal state of an object and restricts access to only necessary methods. We explored how encapsulation enhances data integrity, security, and maintainability through controlled access to class variables and methods. Furthermore, we discussed the relationship between encapsulation, cohesion, and coupling, emphasizing the importance of clear interfaces in software design. Now we will cover how Android's UI elements operate as classes, allowing us to leverage the full power of Java in building engaging interfaces. Next, we will write a simple Android activity that utilizes a button to change the text of a text view when clicked. In the code, we first define our main activity class, extending app-compat-activity, which is a common practice as it provides compatibility support for older Android versions. We declare a private variable for our text view, allowing us to manipulate its contents later. Within the onCreate method, we call setContentView to link our activity with the corresponding XML layout, ensuring our UI elements are displayed. We then use findViewById to obtain references to our text view and button, which have been defined in the layout XML file. To make our button functional, we implement its click listener using setOnClickListener. This listener triggers an anonymous inner class where we override the onClick method. Here, we instruct the application to change the text in our text view to text changed whenever the user clicks the button. This demonstrates how interactive components are managed in Android, reinforcing the idea of encapsulation and user interactivity within your app structure. Now let's take a look at how we can implement a linear layout to organize multiple buttons within our Android app. In this example, we start by defining a linear layout with XMLNS Android to reference Android's attributes. We specify Android layout width as match parent so that the layout spans the entire width of its parent container, while Android layout height is set to wrap content to ensure it only takes up as much vertical space as needed. Inside the linear layout, we add two buttons. Each button is assigned a unique ID for reference, button 1 and button 2. By setting both buttons' layout widths to match parent, we ensure they stretch across the full width of the linear layout. The layout height is set to wrap content, allowing the buttons to adjust their heights according to the text they display. For instance, the text button 1 and button 2 will be displayed on each button respectively. This structured approach not only creates a visually appealing arrangement of buttons, but also helps manage their interactions effectively. Grouping UI elements within a parent layout like this is fundamental in developing an intuitive user interface in Android applications. Next, we will write the following code to implement a switch UI element in our Android application. First, we define the switch in our XML layout file, specifying its ID, layout width, height, and text. This setup allows users to toggle between two states, essentially enabling or disabling a feature with a simple flick. Now let's implement the functionality in our main activity. We retrieve the switch using its ID and assign it to a variable. The onCheckChangeListener is then set up to monitor changes in the switch's state. This listener triggers the onCheckChanged method, which reacts whenever the switch is toggled. Inside this method, we check whether the switch is in the on or off position by evaluating the isChecked Boolean value. Depending on this state, we update a text view to inform users of the switch's current status. This instant feedback enhances the user experience, showcasing the importance of responsive UI elements in app development. With these simple steps, we've successfully added interactive functionality to our app. Now let's see how we can implement a button with a customizable background based on user interactions. We start by defining a button in our XML layout. The Android background attribute references a drawable resource pointing to a file named button background, XML. This drawable will consist of a selector, allowing us to specify different backgrounds for various button states, such as when it is pressed or inactive. Next, we create our drawable resource. This XML file defines a selector element, which holds a set of item elements that dictate the button's visual response. The first item specifies a color for the button's background when it is in a pressed state. In contrast, the second item sets the default background color when the button is not pressed. By using this selector approach, we can easily manage and switch between appearances based on user actions. Overall, incorporating these techniques helps enhance the user experience by providing visual feedback, allowing the button to react dynamically to interactions while maintaining a unified design throughout the application. This demonstrates the flexibility of Android UI components to create engaging interfaces. Now let's see how we can implement a long-click event for our button, which requires utilizing the onLongClick Listener interface. In the code, we first retrieve the button using findViewById by referencing its ID. This establishes our connection to the button key delegated to respond to user interactions. Next, we set an onLongClick Listener on the button, which allows us to define what happens when the button is pressed for an extended duration. Within the listener, the overridden onLongClick method is where the action takes place. When the button is long pressed, this method is triggered, and we update the associated text view to display a message indicating the button's long-click action. It's important to note that we return true at the end of this method. This signifies that we have fully handled the long-click event, preventing further actions from occurring. This not only caters to user interactions effectively, but also helps create a responsive and engaging user interface, enhancing the overall experience within the application. Now let's take a look at how we can implement a constraint layout in our XML. This layout allows us to create complex user interfaces while maintaining a flat view hierarchy, which improves performance. In our code, we define a constraint layout as the parent element, setting its width and height to match the parent's dimensions. Inside this layout, we place a button with a unique ID, enabling reference to it within our Java code. The button's layout width is set to 0 dp, which will allow it to expand based on defined constraints, making it responsive across various screen sizes. To ensure proper positioning, we use a series of layout constraint attributes. For instance, the button is constrained to the top of the parent layout and aligned with both the start and end edges, allowing it to remain centered regardless of device orientation or screen size. By leveraging constraint layout, you can facilitate the creation of more intuitive designs and use fewer nested views, ultimately leading to a more efficient UI architecture. This approach not only streamlines your layout, but also enhances the user experience by ensuring that your app looks and behaves consistently across different devices. Now let's take a look at how to enhance the accessibility of our Android application by adding content descriptions to our UI elements. In the given code, we define a button that opens the next activity and assign it an Android content description. This content description serves as an essential identifier for assistive technologies, such as screen readers, allowing users with visual impairments to understand the function of the button. When we declare the button in our layout XML, we specify its dimensions, text label, and accessibility information. The use of Android content description is crucial because it conveys the purpose of the button to users who might not be able to see it, ensuring inclusivity in our application's design. By adding this feature, we not only comply with accessibility best practices, but also enrich the user experience for all potential users. Incorporating such features into your Android UI elements is a vital step toward creating applications that are welcoming and usable by everyone, regardless of their abilities. By now, you should have a clearer understanding of how Android UI elements are represented as classes and how they can be manipulated to enhance user interactions. From buttons to layouts, each class comes equipped with methods and properties that provide fantastic flexibility and control in your designs. Remember, each UI component is more than just a visual placeholder. It is a class built upon decades of object-oriented programming principles, encapsulating behaviors and properties that create the immersive experience users expect. Embrace these concepts as you embark upon your journey to building incredible Android apps. As you continue to practice and build, think about how you can apply what you've learned here, utilizing classes to their fullest potential to make your apps not only functional, but also delightful. Now let's dive into the world of Android widgets and their implementation. Android widgets are essential UI components that enhance user interaction within an app. In this lesson, we will explore various widgets, implement them in Java code without relying on XML layouts, utilize anonymous classes for handling widget interactions, and even integrate our newfound knowledge into a mini app. So far, we learned about the integral connection between Android UI elements and Java classes, emphasizing the interactive nature of components like buttons and text fields. We explored how these elements derive from the view, superclass, and the importance of understanding their hierarchical structure for effective customization. Additionally, we discussed user interaction through event listeners and event handling within these classes, which enhances user experience. Finally, we looked at various layout classes and the significance of accessibility features, ensuring inclusivity in app design. Now we will cover Android widgets, their specific functionalities, and practical implementations in our projects. Now let's take a look at how we can implement a simple button in our Android application. In our main activity, we start by importing the necessary packages, which enable us to use essential components like button, toast, and the activity framework. Within the onCreate method, we create an instance of the button class, specifying the text that should appear on the button with the setText method. Next, we set the button as the view for our activity by calling setContentView, which means that when the activity starts, the button is what the user will see on the screen. The functionality of the button comes to life when we implement an onClick listener. This listener allows us to define a response to the button press. In this case, a toast message appears when the button is clicked, providing immediate feedback to the user. This demonstrates the fundamental interaction concept in Android, where UI elements connect user actions to application responses, ultimately enhancing the user experience in our app. Next, we will implement an edit text widget, which will be crucial for capturing user input in our app. The first step in the code is the creation of a linear layout, allowing us to stack our UI components vertically. This layout paves the way for a clean organization of our widgets, enhancing user experience. Now let's look at how we introduce the edit text instance, where users can type in their text. We then add a button labeled Submit that users can click to send their input. Both of these components are added to the layout using the addView method, layering them in our vertical layout. When the button is clicked, we retrieve the input from the edit text using the getText method. This step converts the input into a string, which we can then use. We provide instant feedback to the user through a toast message that displays the text they entered, showcasing the app's ability to respond to user actions. This interaction emphasizes the seamless connection between user input and application feedback, enhancing overall engagement. Now let's implement a more interactive element by introducing the checkbox. The checkbox provides users with a way to make a binary choice, visually indicating whether an option is selected or not. In our code, we begin by creating a linear layout with a vertical orientation, allowing us to stack our widgets vertically. Next, we add an edit text for user input and a checkbox labeled Agree to Terms. This checkbox gives users the option to agree or disagree with certain terms. We also create a button labeled Submit, which will trigger our action when clicked. By grouping the edit text, checkbox, and button in the layout, we ensure a logical flow for user interaction. Once our layout is set, we utilize the setOnClickListener method for the button. When the button is pressed, we retrieve the input text from the edit text. We also check the status of the checkbox using isChecked, determining if the user has agreed to the terms. Finally, a toast message is displayed, summarizing both the user's input and their agreement status. This showcases how widgets can dynamically respond to user interactions and provide immediate feedback. Now let's see how we can implement radio buttons using a radio group to allow users to make a single selection among multiple choices. In our code, we first create a linear layout to organize our UI elements vertically and set the orientation accordingly. Next, we define a radio group, which acts as a container for individual radio button instances. Here, we instantiate two radio button objects, labeling them as Option 1 and Option 2. After adding these radio buttons to the radio group, we introduce a button for submission. The setOnClickListener for the button captures user interaction. When clicked, it retrieves the ID of the currently selected radio button using the getCheckedRadioButtonId method. This ID helps us to fetch the selected radio button instance and extract its text. If no option is selected, a default message indicating no option selected is displayed. Finally, we use a toast to provide immediate feedback on the user's choice, demonstrating how radio buttons can enhance user engagement by streamlining selection processes. Now let's implement the Spinner, a versatile widget that aids users in making selections from a drop-down menu, helping maintain a clean interface. We start by initializing a linear layout as our primary container, providing a vertical arrangement for our widgets. Next, we create the Spinner and supply it with a list of choices using an array adapter, which simplifies binding data to the Spinner's view. We then introduce a button labeled Submit, which will enable user actions once a selection is made. It's crucial to add both the spinner and the button to our layout to ensure they become part of the app's visible interface. After configuring the layout, we set the content view to our constructed layout, making it appear on the screen. Next, we define what happens when the user clicks the button by adding an on-click listener. In this listener, we retrieve the currently selected item from the spinner and display it using a toast message. This interaction enhances user experience by providing immediate feedback, showcasing the selected choice without cluttering the screen, effectively demonstrating how the spinner streamlines option selection in Android applications. Next, we'll implement the button's click listener using a Lambda expression, which streamlines our code and enhances readability. In this snippet, we set the button's on-click listener to take a click event as an input and define the action that occurs upon clicking. Instead of the traditional anonymous class syntax, we use the cleaner and more concise Lambda notation, represented by the arrow operator. Inside the curly braces following the Lambda, you would place the code that defines the action to be executed when the button is clicked. This approach reduces boilerplate code significantly, making it easier to focus on the logic of what happens during the button click instead of the structural details tied to the old event handling method. By using Lambda expressions, we can create event listeners that are not only more readable, but also less verbose, promoting better code maintainability as our application grows in complexity. This small change can greatly improve how we handle user interactions in our Android applications. In summary, we have traversed through the realm of Android widgets, diving into their functionality and implementation. We started by creating buttons and collecting user inputs via edit text, then expanded our knowledge by adding interaction with checkboxes, radio buttons, and spinners, culminating in a deeper understanding of event handling through anonymous classes and Lambda expressions. We established a mini-app that incorporates all these widgets, showcasing how to capture inputs and produce meaningful outputs based on user interactions. As you continue your journey in Android development, remember that the creativity and functionality of your apps hinge greatly on how effectively you can implement and manage these widgets. With this newfound knowledge, you are well equipped to enhance your applications with interactive elements that genuinely respond to user engagement. Keep experimenting with different widgets to find the perfect combination for your app. Welcome. Today, we're diving into the first of three major applications we'll be building together, the Note-to-Self application. This practical application provides a platform for users to take notes, set reminders, and enhance their productivity. We'll start with the basics of understanding the essential components required to bring this application to life and add some advanced features along the way. So far, we learned about the implementation and functionality of various Android widgets, such as buttons, edit texts, checkboxes, radio buttons, and spinners, highlighting their interactive aspects within apps. We explored event handling techniques, first using anonymous classes and then considering the use of Lambda expressions for cleaner code. Through practical implementations, we gained insights on capturing user input and delivering immediate feedback effectively. As we progress, we will further refine our understanding and explore advanced interaction methodologies in Android development. Now let's implement our layout file, activity main, XML, which is essential for the Note-to-Self application. In this layout, we define a vertical linear layout that organizes our UI elements vertically. First, we include an edit text that allows users to input their notes, ensuring it's multi-line with a minimum height for visibility. This element is crucial as it captures the user's note input. Next, we add a button labeled Add Note, which will trigger the action of saving the inputted note. Finally, we incorporate a Recycler view designed to display the list of notes. Notice that the Recycler view has its height set to 0 with a weight of 1. This ensures it occupies all available space in the layout, providing a clean and structured interface. After setting up the layout, we will move on to the main activity Java file to manage the functionality behind our notes application. Here, we will initialize our views and set up an array list to hold the notes, along with an adapter to facilitate their display. This foundational setup allows for interactive features that enhance user engagement with the app. Now let's see how we can implement the core logic for our Note-to-Self application in the main activity Java file. We start by defining our main activity class, which extends app-compat-activity, a fundamental component in Android development for building activities. Within this class, we declare private member variables for our UI components, an edit text for user input, a button for adding notes, and a Recycler view to display the notes list. Next, we override the onCreate method, which serves as the entry point for our activity. In this method, we initialize our UI components by linking them to their respective views defined in the XML layout. We then instantiate an array list to hold our notes and create an adapter that binds the data to the Recycler view. The adapter enables efficient display and management of our notes. We also set an on-click listener on the Add Note button. When triggered, it retrieves the text from the edit text. If the input is valid and not empty, we add the note to our list and notify the adapter to update the view accordingly. This immediate feedback enhances user experience by allowing users to see their changes reflected seamlessly in the app. Next, we will write the Notes adapter, which is crucial for managing how notes are displayed in the Recycler view. This class extends the Recycler view, adapter, and utilizes the note view holder to represent each note. In our constructor, a list of notes is initialized, allowing the adapter to manage these items effectively. Now, let's see how we can implement the onCreateViewHolder method, which is responsible for inflating the layout for each note. Here, we use the layout inflator to create views that the Recycler view will display. Next, we will explore the onBindViewHolder method. This function binds the note data to each view holder, effectively displaying the content of the notes on the screen. By using the holderBind method, we set the text for each note, ensuring the Recycler view shows the correct information. Now, let's look at the getItemCount method, which returns the total number of notes in the list. This is vital for the Recycler view to understand how many items it is managing. Finally, we will implement the static inner class, NoteViewHolder, which holds the individual note views, maintaining a clear separation between data and view logic within our adapter. Now let's implement the code needed to enable users to delete notes from our application. In the onBindViewHolder method of the Notes adapter, we will enhance user experience by adding a long-click functionality to each note. This function allows notes to be removed from the list with a simple long press, making it intuitive for users to manage their notes. To achieve this, we set an onLongClick listener on the item view of the Note View holder. When a user long-clicks a note, it triggers a callback that removes the note at the specified position from the notes list. Following the removal, we call NotifyItemRemoved, which updates the Recycler view and animates the item's removal efficiently. The use of returnTrue indicates that we have handled the long-click event. This addition not only simplifies the deletion process, but also enhances the overall functionality of our Notes application, ensuring users can easily manage their notes without additional clutter. With this implementation, our app becomes more cohesive and user-friendly, thereby promoting better interaction with the note-taking platform. Now let's implement the Database Helper class, which will play a crucial role in managing our notes. This class extends Sqlite Open Helper, and within it, we define constants for the database name, version, and the notes table. The constructor initializes the database, and in the onCreate method, we define the schema by creating a table to store notes, including an ID and the note text itself. Next, we override the onUpgrade method, which will drop the existing notes table if there is a version change, ensuring that all notes are updated. To enhance functionality, we implement three key methods: addNote, getAllNotes, and deleteNote. The addNote method allows us to insert new notes into the database using content values. The getAllNotes method retrieves all stored notes, leveraging a cursor to iterate through the results, while deleteNote removes specified notes by executing a delete command. This structured approach to database management ensures that our application maintains data persistence effectively, allowing users to keep their notes across sessions. Now let's integrate the database functionality with our main activity. Here, we start by declaring the necessary attributes, including an instance of the database helper, along with the existing views such as the edit text, button, and Recycler view. In the onCreate method, we initialize these views as before, but now we also instantiate the database helper, which will manage our Sqlite database interactions. Next, we retrieve existing notes from the database using the getAllNotes method, ensuring that users see their saved notes as soon as they open the application. After setting up the Notes adapter with the retrieved notes list, we attach it to the Recycler view. This effectively binds our UI with the data. When a user adds a new note by clicking the button, we check if the input is non-empty. If valid, the note is added to the notes list, and the addNote method from our database helper is called to store it in the database. Finally, we notify the adapter of this change, updating the UI seamlessly. This ensures that our note-taking application is robust, allowing for data persistence and a smooth user experience. Now let's see how we can implement the editing functionality in our Notes adapter. We start by setting an onClick listener on each item in the Recycler view. when users tap on a note, an alert dialog pops up, allowing them to edit their note. Inside the dialog, we create an edit text pre-filled with the existing note, enabling users to see and modify its content. Next, we provide two buttons in the dialog, Update and Cancel. When the Update button is clicked, we retrieve the updated text from the edit text. If the input is not empty, we replace the old note in the list with the new one, notify the adapter to refresh the displayed list, and update the database by deleting the old note and adding the new one. This ensures that the database reflects the most current state of the notes. If the user chooses Cancel, the dialog simply closes without making any changes. This interactive feature enhances the user experience, making it easy for users to manage their notes directly within the application. Now let's implement a feature that allows users to share notes seamlessly. In the Notes adapter, we need to set an on-click listener for each note item that the user can interact with. When a note is clicked, an intent is created using intent action send, which prompts the shared dialog. We specify the MIME type as text plain to indicate we are sharing text content. The text of the note to be shared is then passed using putExtra, which adds the note at the selected position in the list to the intent. By calling startActivity with intent create chooser, we present the user with a dialog showing all compatible applications available on their device, allowing them to choose how they want to share their note, whether through email, messaging apps, or social media platforms. This simple implementation significantly enhances our app's functionality, enabling better user engagement by allowing users to easily share their notes with others. We have built a fully functional note-to-self application that allows users to create, view, delete, and edit notes while also storing them persistently using Sqlite. Today, you've learned to implement layouts, manage recycler views, and create a database helper for data storage. We've interacted with the user's input and created a fluid interface that is easy to navigate, demonstrating strong Android development practices. Remember, our journey doesn't end here. Continue exploring advanced topics, such as optimizing our application for performance or implementing additional features like categorizing notes, adding notifications, or even syncing with cloud storage. Keep experimenting and coding, and you'll elevate your Android development skills beyond measure. Thanks for joining me today, and in this video, we're diving into the essentials of handling and displaying arrays and array lists in Java. Ready to get started? Let's go. So far, we learned about the development of the note-to-self application, focusing on creating a note-taking platform with features for adding, viewing, editing, and deleting notes. We implemented various UI components like edit text, button, and recycler view, along with user interaction handling through event listeners. Additionally, we integrated data persistence using Sqlite for storing and managing notes. Overall, we've established a robust foundation for further enhancements and advanced functionality in Android development. Now, we will cover how to effectively utilize arrays and array lists to manage data in Java applications. Now let's implement a fixed-size array to store our notes. In the first example, we declare an array called notes that is intended to hold 5 string objects. This declaration specifies that we want an array to contain textual information, but it's important to remember that the size is defined at this stage and cannot be changed later. This characteristic of arrays can be both useful and limiting, depending on the application. Next, we will create another array initialized with values directly. In this case, we set up our notes array with 3 predefined notes. This method of initialization provides immediacy and clarity for the data we plan to manage, allowing us to work with specific content right from the start. Now let's see how we can access individual elements within our array. By using an index, we can retrieve specific notes. For instance, note 0 will give us the first note, which is note 1. This zero-based indexing is key in Java, as it allows us to efficiently refer to elements in the array. Lastly, if we want to update an item within the array, we can do so by targeting its index. For example, to change the second note to updated note 2, we simply assign the new text to the desired index. This ability to modify elements demonstrates how arrays help in managing structured data efficiently. Now let's take a look at how to create and use an array list in Java. First, we begin by importing the necessary class from the Java Collections framework, which allows us to leverage the powerful functionality of array lists. Declaring our notes list, as an array list of strings will initiate an empty list ready to store our notes. We can easily add notes using the add method, showcasing how straightforward it is to populate our list dynamically. Next, we will enhance our list by creating another array list called additional notes. This allows us to gather multiple new notes, which we can effectively merge into our primary notes list with the add-all method. This demonstrates the flexibility of array lists, as they can accommodate bulk additions seamlessly. Once we have notes in our list, we now focus on how to access them. By using the get method with an index, we can retrieve specific notes, such as the second one. Finally, we will see how to manage our notes by removing one with the remove method, highlighting the ease of modifying the contents of our list. This flexibility is key to creating dynamic applications like our note-taking platform. Now let's take a look at how we can create a custom class to represent our notes effectively. The note class is designed to encapsulate the properties of each note, specifically the title and content. By defining private member variables for title and content, we ensure that these properties can only be accessed through the provided public methods. This encapsulation promotes better data management and enhances the robustness of our application. Next, we will implement an array list to store our notes as objects of the note class. By creating an array list note called noteslist, we can dynamically add new notes to our collection. For instance, we can instantiate new note objects and add them to the list using the add method. This allows us to maintain an organized set of notes without worrying about the fixed size constraints that arrays impose. To display the details of each note effectively, we will utilize a for each loop to iterate through noteslist. This method not only simplifies the iteration process, but also enhances readability by allowing us to access each note's properties seamlessly. By printing the title and content of each note, we can provide users with a clear and organized view of their notes in the application. Now let's take a look at error handling when working with array lists in Java. In this example, we attempt to access an element at a specific index in the array list named noteslist. Since array lists are dynamic and allow for frequent additions and removals of items, there's a risk of trying to access an index that does not exist, which could lead to an index out of bounds exception. To prevent your application from crashing and to handle such scenarios gracefully, we can encapsulate the access attempt within a try block. If the index we're trying to reach is invalid, the code catches the exception through a catch block, where we can respond appropriately. In this case, the catch block displays a message to inform the user that the note does not exist. This practice of implementing error handling not only enhances user experience, but also embodies a fundamental principle of robust application development, ensuring that your application can handle unexpected situations without failing completely. By incorporating this mechanism, your application will continue to function while providing informative feedback to the user. Now let's take a look at how we can effectively traverse an array and an array list to display their contents. For an array, we can utilize a for each loop, which is a clean and efficient way to iterate through each element. In this case, for each note in our array, we simply print the note to the console. This method makes it easy to understand the structure of our data while maintaining readability in our code. Next, we will implement the same traversal logic using an array list, but with the added flexibility of an iterator. By creating an iterator for our notes list, we gain fine-grained control over the iteration process. The iterator allows us to check if there are more elements to process and retrieve each note sequentially. This approach is particularly beneficial as it enables us to remove elements from the list during iteration without causing a concurrent modification exception, which can occur if we modify the list using regular iteration methods. This practice highlights the advantages of using iterators with data structures, especially when managing dynamic collections like array lists. Now let's take a look at how we can sort our notes in a user-friendly manner. To achieve this, we utilize the collection sort method, which allows us to organize our array list of notes based on their titles. This written code snippet introduces a custom comparator by leveraging Java's anonymous inner class capabilities. In this example, we define the compare method, which takes two note objects as parameters, n1 and n2. The method uses the getTitle function, which retrieves the title of each note, and then applies the comparator method to compare the titles lexicographically. This means notes will be sorted in alphabetical order, enhancing the clarity and structure of how the notes are displayed to users. Utilizing this sorting mechanism not only streamlines user interaction, but also helps in organizing information effectively, making it easier for users to locate their desired notes quickly. Overall, implementing this sorted feature significantly improves the usability of the note-to-self application. In summary, arrays and array lists are pivotal in managing collections of data in Java applications. We've explored how to declare and manipulate arrays, transitioning into the more dynamic and flexible array lists. You learned how to create custom data types, ensure error handling, and utilize iterative techniques for effective data management. Whether you're developing a simple application or a complex one like the Note-to-Self platform, mastering arrays and array lists is indispensable for efficiency in your coding practices. With this newfound knowledge, you're well prepared to enhance the functionalities of your applications, implement data persistence effectively and create a more user-friendly experience. Now let's implement the Notes Adapter class, which is responsible for bridging the data source with the list view. This adapter takes a context and an array list of strings representing our notes. First, we need to define the crucial methods of the adapter, starting with getCount, which returns the total number of notes available, allowing the list view to know how many items to display. Next, the getItem method retrieves the note at a specified position, while getItemId simply returns the position as the unique ID for each item. The most important part of the adapter is the getView method, which creates and configures the view for each item in the list view. In this method, we check if the view can be reused with convertView. If not, we inflate a new layout using our defined XML. We then access the text view within the inflated layout and set its text to the appropriate note. This structured approach allows for efficient memory usage and smooth scrolling performance in the list view, as views are reused instead of created from scratch each time. With our Notes adapter ready, we can integrate it into the main activity to display the notes dynamically. Now let's implement the custom adapter by creating the Notes Adapter class that extends base adapter. This class is crucial as it connects our list view with the data set, in this case an array list of notes. We begin by initializing the adapter with the required context and the list of notes. The getCount method serves to return the total number of notes, allowing the list view to render the correct amount of items. Next, the getItem and getItemId methods help retrieve specific notes and their associated IDs based on the position in the list, ensuring each note can be uniquely identified. The core of the adapter's functionality lies in the getView method, which is responsible for generating the view for each item displayed in the list view. Here, we inflate the layout for a single note and assign the note text to the corresponding text view. This method also checks if a recycled view is available to optimize performance by reusing existing views instead of creating new ones, which significantly improves scrolling efficiency in the list view. Through this implementation, the Notes adapter neatly encapsulates the logic for displaying the notes, maintaining a clear separation of concerns in our application. Now that we have established our layout for displaying notes, let's proceed to implement the functionality within our main activity. Here, we define the main activity class, which serves as the entry point to our application, where we will handle interactions with the list view. Next, we will write the code to initialize our list view and bind it with our Notes adapter. In the onCreate method, we start by invoking setContentView to set the layout for the activity. We then obtain a reference to the list view defined in our XML layout using findViewById. With the list view set up, we create an array list to hold our notes and instantiate our custom Notes adapter, passing in the context and the notes list. Finally, we attach the adapter to the list view using setAdapter, which makes our notes list visible on the screen. Additionally, we need a way to add new notes. This is handled by the addNewNote method, which adds a string representing a note to our array list and calls notifyDataSetChanged on the adapter. This call refreshes the list view, ensuring it displays the most current notes as additions are made. Now let's implement interactive functionality for our notes by adding item click handling for the list view. To achieve this, we need to set up an onItem click listener for the list view. This listener will respond to user interactions, specifically when a note is clicked. Within the listener, we can retrieve the clicked note using the position parameter, which corresponds to the item in the notes array list. Once we have the selected note, we can create a simple user feedback mechanism by displaying a toast message that confirms the selection. This feedback enhances user interaction, making the app feel more responsive and engaging. Next, let's consider how to extend the functionality to include long press actions for deleting notes. We need to implement another listener, onItem onClick listener, on the list view. In this listener, when the user long presses an item, we can remove the corresponding note from the array list and update the adapter to reflect this change in the list view. To notify the user of the successful deletion, we can again utilize a toast message. This interaction not only reinforces user engagement, but also streamlines note management, allowing users to effectively curate their notes. Next, we will implement the functionality that allows users to delete notes through a long press action in the list view. To achieve this, we set an onItem onClick listener on the list view, which triggers when a user long presses a note. In the listener's callback, we first remove the note from the array list using its position, ensuring that the corresponding item is deleted from our data structure. After that, we call adapterNotifyDataSetChanged to refresh the list view, which visually updates the displayed items to reflect the current state of our notes. Finally, we provide user feedback by displaying a toast message that confirms the note has been deleted. This approach not only effectively manages note removal, but but also enhances user experience by instantly communicating the action's success, reinforcing interactivity in our Note-to-Self app. By allowing users to delete notes with a simple gesture, we streamline note management, making it more intuitive and user-friendly. Now let's implement the method to save our notes so that they persist even after the app is closed. The Save Notes method makes use of a file output stream to create and write to a text file named notes.txt in private mode, ensuring that the data is only accessible to our app. As we iterate through the notes list, each note gets written into the file followed by a newline character, making them easy to distinguish when we read the file later. Once we've successfully written all notes, we close the file stream to save our changes. Error handling is also an essential part of this process. Should any I/O exception occur, perhaps due to device storage issues, we catch that exception and print the stack trace for debugging. A user-friendly toast message is displayed to inform the user whether the notes were successfully saved or if an error occurred. This method not only encapsulates the file writing logic, but also enhances user experience through immediate feedback, reinforcing the importance of combining functionality with usability in mobile applications. Now let's take a look at how to implement the loading function for notes in our application. The load notes method starts by attempting to access the notes.txt file through a file input stream, which allows us to read previously saved notes. To efficiently read the file line by line, we use a buffered reader wrapped around an input stream reader. Each line read from the file is then added to the notes array list after clearing any existing content to prevent mixing old and new data. Once all lines are loaded, we close the input stream to preserve system resources and update the list view by calling adapt-to-notify-date-set-changed, which refreshes the display to reflect the newly loaded notes. Additionally, we provide feedback to the user by showing a toast message indicating that the notes have been successfully loaded. Error handling is incorporated using a try-catch block, which helps manage any issues that might arise during file operations, ensuring that users are notified if there is an error loading the notes. This method is essential for offering a seamless experience, allowing users to retrieve their notes effortlessly as they restart the app. At this point, we have developed an interactive Note-to-Self app capable of handling and displaying a vast number of notes with ease. We've integrated key functionalities like adding, displaying, deleting, and saving loading notes, all while enhancing user interaction with a dynamic list view. Each section of our code is designed to be modular and reusable, following best practices for Android development. In our next steps, we can explore how to further enhance the user experience by adding features like editing existing notes, categorizing notes, or even integrating a search function. These enhancements will not only improve usability, but also provide an opportunity to learn more about Android development and data management. As we wrap up this session, I encourage you to play around with the code, experiment with different functionalities, maybe add a feature that allows users to prioritize notes or stylize the list view even further. Keep exploring and remember, the only limit is your imagination. At this point in our journey through Android development, we're ready to elevate our Note-to-Self application by delving into Android intents and persistence management. We are about to explore powerful features that will enhance user interactions and ensure data lasts beyond the app's runtime. So far, we learned about developing the Note-to-Self application, focusing on effective note management through Java arrays and array lists. We implemented a list view and a custom base adapter to display user notes and added functionality for users to interact with, including adding and deleting notes. The application now supports saving and loading notes to and from a text file, ensuring data persistence. Next, we will explore further enhancements to improve user experience and application functionality. Now let's see how we can implement the necessary setups for our edit note activity. We start by declaring the new activity in our Android manifest XML file. This declaration informs Android about our activity, allowing it to be recognized and launched when needed. Next, we create an intent in our main activity to navigate to the edit note activity. By invoking the intent constructor with our current activity context and the target activity class, we establish the connection necessary for the transition. The putExtra method is used to pass the specific note data we want to edit, attaching it as an extra to our intent. This allows edit note activity to retrieve the information it needs to display the correct note for editing. Now let's take a look at how we will handle the data in edit note activity. Upon creation of this activity, we will access the intent that started it, extracting the note using getStringExtra. If a note is found, we set it into our edit text field, providing the user with the relevant content to modify. This flow highlights how intents facilitate seamless data transfer between activities, enhancing user interaction and providing a cohesive experience. Now let's take a look at the Edit Note activity, where we handle the editing of notes. In this activity, we begin by setting up the user interface and linking our Edit Text field to the layout resource. This allows us to display the note that the user has selected for editing. Once the activity is created, we utilize the getIntent method to retrieve the intent that started this activity. By using the getStringExtra method, we can extract the note data passed from the previous activity using the key note key. This facilitates smooth data transfer between activities. If a note is found, we set the text of our Edit Text field to the retrieved note, enabling the user to see and edit their content. Thus, this code demonstrates the efficient use of intents for passing data between activities and enhances user experience by allowing easy modification of notes. By understanding how to manage intents and extract data in this way, we can create a seamless editing interface within our note-to-self application. Now let's implement the functionality to save the updated notes in our Edit Note activity. First, we set up a Save button and attach an on-click listener to it. When the button is clicked, we retrieve the user input from the Edit Text field, which contains the edited note. We create a new intent to prepare for passing this updated data back to the main activity. By using the putExtra method, we assign the updated note to a key, which can later be accessed in the main activity. After that, we call setResult, result OK, result intent, to signal that the operation was successful and to send our result back. This is crucial for facilitating communication between activities. To conclude this process and return to the main activity, we invoke the finish method, which ceases the current activity. Next, we must handle this result in the main activity. When we override the onActivityResult method, we check if the result comes from our Edit Note activity and confirms it was successful. Here, we extract the updated note from the returned data and can then proceed to update our displayed notes, ensuring that the user's edits are effectively preserved and reflected in the app's interface. Now let's implement the Notes Database Helper class to manage our Sqlite database for persistence. This class extends Sqlite Open Helper, which is essential for creating and managing our database. We start by defining constants for the database name, table name, and the columns we will use. The constructor initializes the database and sets its version. Next, we need to override the onCreate method, where we establish the table's structure. Here, we create a table named NoteStable that consists of two columns, an auto-incrementing primary key and a text column for storing the notes. This step sets the foundation for how our notes will be stored. We also implement the onUpgrade method to handle any updates to the database schema, ensuring that if the structure changes, the previous table is dropped and a new one is created. With these methods in place, we ensure that our application can handle the storage and retrieval of notes effectively, paving the way for smooth persistence management as users interact with the app. Now let's look at how to insert a new note into our database. The addNote method is crucial for saving notes persistently as it opens the database in write mode, allowing us to make modifications. We begin by creating an instance of Sqlite database through getWritable database. This instance facilitates access to our Sqlite database for writing data. Next, we prepare the note content by populating a content values object with the note string. This content values object serves as a map, associating the string with the relevant column in our database table. Once prepared, we execute the insert command using db-insert, which adds the note into our specified table. Finally, we close the database connection with db-close, ensuring that all resources are released properly and the data is safely stored. Now let's see how we can retrieve all notes from the database. The getAllNotes method provides an efficient way to extract stored notes. We initiate by creating an empty Arraylist to hold the notes as we collect them. By invoking getReadableDatabase, we gain read access to our database, followed by executing a raw SQL query to fetch all entries from our notes table. Using a cursor, we iterate through the results. If records are found, we extract each note string using the appropriate index and add it to our Arraylist. After processing, we close the cursor and the database connection, returning the list of notes to ensure they can be displayed in our app's user interface. Now let's implement the code necessary to load our saved notes from the database when the app starts. In the onCreate method of the main activity, we begin by calling the superclass's onCreate method to ensure proper initialization. Then, we set the content view to the layout for the main activity, making the interface visible to the user. Next, we create an instance of our Notes Database Helper, which will manage our database interactions. This helper class allows us to organize and access our notes efficiently. We then retrieve a list of all saved notes by calling getAllNotes on our db-helper object. This method executes a query to fetch notes stored in the database and returns them in a convenient list format. Finally, we should update our list view adapter with the retrieved notes so that they are displayed to the user upon launching the app. By initializing the database helper and loading notes like this, we ensure users see their most recent data without needing to take any additional steps, enhancing the overall user experience. In conclusion, intents and persistence management are cornerstones in developing a robust Android application. By utilizing intents, we manage our app's navigation and data transfer seamlessly, enriching user interactions. Combined with data persistence techniques like Sqlite, we ensure that user data remains intact across app restarts, providing a more reliable and professional experience. As we've seen, coding is all about creating connections between activities, data, and users. Embrace these tools, and you'll be well on your way to building impressive Android applications that users will love. Keep experimenting, continue coding, and remember, every small change can lead to significant improvements. Creating engaging user interfaces with Android animations is an exciting way to enhance user experience and make applications more dynamic. Today, we're diving into how to use the animation class effectively to make our UI come alive. So far, we learned about enhancing the note to self-application through Android intents and persistence management. We implemented a mechanism for navigating between activities, allowing users to edit their notes seamlessly, and ensured that note data is saved persistently using Sqlite. The integration of these features enhances user interaction and experience within the app. Next, we will explore how to animate UI elements to make them more appealing and engaging. Animations in Android not only capture users' attention, but can also help them understand how to interact with your app better. When we add animations, we can visually convey transitions, status changes, and responses to user interactions, providing feedback that is essential for user satisfaction. So how do we get started? Let's see how we can bring some fun to our UI through animations. Now let's take a look at how we can create a simple fade-in animation through XML. In this snippet, we define a set of animation properties under setTag, which is required to group animations together. The XMLNS Android attribute specifies the namespace for Android attributes, and the Android fill after equals true property is particularly important as it ensures that once the animation completes, the UI element remains in its final state, fully visible in this case. Within the set, we incorporate an alpha tag that specifies the alpha transition. Here, Android from alpha equals 0, 0 indicates that our UI element starts completely transparent, while Android to alpha equals 1, 0 signifies that it will end fully opaque. The Android duration equals 500 attribute defines the animation's length at 500 milliseconds. This structure not only organizes our animation, but also separates design from code, making future adjustments straightforward. After saving this XML file in the res/anim directory, we can reference it easily in our Java code to implement this engaging fade-in effect for our UI elements. Now let's implement the following code to bring our fade-in animation to life within our Android application. First, we utilize the animation utils class to load our XML-defined animation resource, which we've named fade-in. This is done by calling the loadAnimation method and passing in the application context alongside the resource identifier for our animation. By doing this, we ensure that our animation gets properly initialized before we apply it to any UI elements. Next, we create a reference to the image view that will display our animation. This is achieved by using the findViewById method, where we specify the RID image view, pointing to the unique identifier we set in our layout XML file. With our animation loaded and the image view referenced, we can trigger the fade-in effect by invoking the startAnimation method on our image view object, passing in the loaded fade-in animation. This action initiates the transition from transparency to full visibility, making our UI element more dynamic and engaging for the user. This clean separation between design and logic allows for readability and maintainability in our animation implementation. Now let's see how we can implement a translate animation to move an object from off-screen into view. The XML snippet you'll define contains a translate element that specifies two key properties, fromXDelta and toXDelta. The fromXDelta is set to -100%, indicating that the object starts completely off-screen to the left. The toXDelta is set to 0%, meaning that the target position brings the object back to its original location on the screen. Additionally, the duration property controls how long the animation lasts, which is set to 500 milliseconds in this case, making for a smooth transition. Next, we will write the Java code necessary to apply this animation within our application. We will first load the defined animation from our XML resource using animation utils, load animation, which allows the application to instantiate the animation we created. After that, we'll select the UI element we want to animate, here represented by a button with an ID of button. Finally, we will call Start Animation, Move In, on the button to trigger the animation, making the button smoothly move into view as intended, enhancing the interactivity of our app and providing visual feedback to the user. Now let's implement a scaling animation to enhance our user interface. First, we define the scaling animation in XML, where we specify the scaling factors through the fromXScale and toXScale attributes. In this case, the widget starts at its original size scaled to 1 and grows to 1.2 times its size, creating an engaging effect. The PivotX and PivotY attributes establish the center point around which the scaling occurs, ensuring that the growth is centered. The duration of this animation is set to 300 milliseconds, making the effect noticeably smooth and quick. Next, we can apply this scaling animation in our Java code using the AnimationUtils class, which allows us to load the animation resource we created. We reference the widget we want to animate, which is a text view in this example. By calling Start Animation on the text view, we trigger the scaling effect, providing users with immediate visual feedback that indicates the widget is ready for interaction. This not only enhances usability, but also draws the user's attention to important elements in the application. Now let's take a look at how we can combine multiple animations to create a more dynamic effect in our user interface. In the first part of the code, we define a set XML tag that groups animations together. This allows us to specify that the alpha, fade-in animation and the translate, move into position animation should occur simultaneously. The alpha property transitions the element's transparency from completely invisible to fully visible over a duration of 300 milliseconds, while the translate animation moves the element from the left of the screen into its original position. To implement this combined animation in our Java code, we load the defined animations using the AnimationUtils load animation method. This approach not only ensures that we can easily manage complex animations in our app, but also helps create a seamless user experience by layering animations together. By calling the Start Animation method on our image view, we trigger both the fading and moving animations at the same time, resulting in a visually appealing effect that enhances user interaction on the app's interface. Now let's take a look at how we can incorporate delays into our animations to enhance user experience. Using the Android StartOffset property allows us to introduce a delay before the animation begins, creating a sense of anticipation for the UI elements. For instance, in our example of a fade-in animation, we set the Android StartOffset to 500 milliseconds. This means the fade-in effect will start after half a second of waiting, allowing users to focus on the overall layout before the transition begins. By adjusting the fromAlpha and toAlpha properties, we dictate that the element starts from a fully transparent state and transitions to a fully opaque state over a duration of 500 milliseconds. This smooth transition ensures that the appearance of UI elements feels seamless and visually pleasing. Such controls can significantly enhance the user interface, making interactions feel fluid and engaging. In your Java code, you can modify these properties programmatically if needed, giving you the flexibility to create dynamic and responsive animations tailored to your application's needs. Now let's implement the following code to handle animation events in our Android application. By setting an animation listener on our animation, we can gain insight into the animation's lifecycle, allowing us to execute specific actions at key moments. Within the code, we define an anonymous class that implements the animation listener interface. This interface has three methods: onAnimationStart, onAnimationEnd, and onAnimationRepeat. The onAnimationStart method is triggered when the animation begins, providing an opportunity to execute code that may be necessary for visual or functional adjustments, such as disabling a button to prevent user interaction during the animation. The onAnimationEnd method is called when the animation completes, where we can re-enable the button or perform other actions indicating that the animation has finished. Lastly, if the animation is set to repeat, the onAnimationRepeat method allows us to handle any necessary actions each time the animation restarts. This mechanism enables us to create a more interactive and responsive user experience, where the app reacts appropriately to ongoing animations, enhancing the overall engagement of the application. Now let's take a look at how we can enhance our fade-in animation with an interpolator. Interpolators are crucial for adding a layer of realism to our animations by controlling their pace. In our code, we define a fade-in effect by starting with an alpha value of 0, which means the element is completely invisible, and transitioning to an alpha of 1, which makes it fully visible. The duration of this transition is set to 500 milliseconds, giving users a smooth visual experience. To enhance this fade-in effect further, we utilize an interpolator. By specifying Android interpolator equals at Android anim/accelerate interpolator, we instruct the animation to begin slowly and then accelerate towards the end. This simulates a more natural movement, allowing the element to appear in a way that feels more fluid and engaging. The combination of these properties not only makes the animation visually appealing, but also enhances user interaction by guiding their attention effectively. With this understanding, you're now equipped to implement more dynamic animations that bring your user interface. Now let's dive into the exciting world of sound effects in Android. Sound effects can significantly enhance your applications, making them more engaging and fun for users. Today, we'll explore loading and playing sound effects using the SoundPool class, and we'll discuss how to ensure compatibility with various Android versions. So far, we learned about creating engaging user interfaces with Android animations to enhance application interactivity and user experience. We explored using the animation class to implement various effects, including fade-ins, translations, and scaling animations. We discussed the importance of timing, event listeners, and interpolators to add realism and control to animations. These techniques allow developers to create dynamic and appealing user interfaces that respond gracefully to user interactions. Now, we will talk about sound effects and how they contribute to a rich, interactive user experience. Now, let's implement the initialization of the sound pool, taking into account the Android version to ensure compatibility. First, we check if the device is running on Android Lollipop, API level 21 or above. If it is, we'll create an audio attributes object. This object is essential as it allows us to configure how the application intends to use the sounds, particularly by specifying that they are meant for media usage and tagged as sonification content. With these attributes defined, we instantiate the sound pool using a builder pattern. This method not only specifies the maximum number of simultaneous streams, but also incorporates the audio attributes we've previously set up, enhancing sound playback. For devices running an earlier version of Android, we have a simpler initialization process. Here, we directly create the sound pool object with the older constructor, specifying the maximum number of streams and the audio stream type as music. This approach is straightforward and ensures that our application remains functional across different Android versions, providing a seamless experience regardless of the device's capabilities. Now let's implement the following code to load sound effects into the sound pool. First, we initiate an asset manager, which allows access to our sound resources stored in the assets directory of our application. Utilizing the openFD method, we open a specific sound file, in this case, sound file, OGG. This method returns an asset file descriptor that is essential for loading the sound file into memory. The next step is to call the load method of the sound pool, passing the descriptor and a priority level, which we set to 1 for basic sounds. This prioritization helps manage playback efficiently, even when multiple sounds are triggered simultaneously. Additionally, error handling is implemented with a try-catch block to manage any potential I/O exception that could arise from file access issues, ensuring our application runs smoothly without crashing. Once your sound has been successfully loaded, we can easily play it using the play method of the sound pool. Here, we specify the sound ID obtained from loading the sound file, setting both the left and right volume to 1 to achieve full sound output. We also indicate the priority, 0 for normal playback, set the repeat count to 0 to play the sound once, and maintain a playback rate of 1 for normal speed. This straightforward approach to playing sound effects enhances the interactive experience for users. Now let's see how we can stop a sound effect that is currently playing. The method used for this is straightforward. It involves calling the stop method of the sound pool object. To identify which sound to stop, you pass the sound ID as an argument to the method. This is crucial when your application manages multiple sounds, allowing for precise control over audio playback. Stopping sounds effectively enhances the user experience by preventing unwanted overlaps or interruptions, which can detract from the overall engagement of your application. Efficient audio management is particularly important as your application becomes more complex and users may trigger various sound effects simultaneously. Therefore, understanding how to control sound playback, including stopping sounds when necessary, is a vital skill in developing polished Android applications. As you continue building interactive experiences, keeping track of your sound resources and managing them wisely is key to delivering a seamless auditory experience. Now let's see how we can implement conditional checks for Android versions to ensure compatibility with the SoundPool class. The first logical step is to check the device's current Android version using the build version SDKINT. For devices running Android Lollipop, API level 21 or above, we utilize a new sound pool configuration method that includes setting up an audio attributes object. This object allows us to specify how the sounds will be used, enhancing audio management by making it more efficient for media playback. In contrast, for devices running versions below Lollipop, we need to apply the older sound pool constructor, which does not support these advanced features. This approach allows our application to gracefully accommodate both modern and older devices, ensuring that all users, regardless of their Android version, can enjoy the sound effects functionality of the application. By writing conditional code in this way, we not only enhance compatibility, but also future-proof our app for subsequent updates and changes in Android's audio handling capabilities. This attention to detail can have a significant impact on user experience across a wide range of devices. To summarize, we've explored how to load and play sound effects in Android using the sound pool class. We've looked at initializing sound pool differently based on the Android version, how to load sound files, and the method to control playback, including stopping sounds. As we continue our journey in Android development, remember that sound effects play a crucial role in enhancing user interaction. It's about creating an engaging experience where users can feel and hear the application responding to their inputs. So go ahead, integrate sound effects smoothly, and take your Android apps to the next level. And don't forget, practice makes perfect. Try experimenting with different sound effects and scenarios in your apps to truly appreciate them. Fragments are a crucial part of Android development, allowing for modular UI components that facilitate dynamic user experience. By using fragments, developers can create flexible layouts that adapt to different screen sizes and orientations. In this lesson, we will dive deep into the understanding of fragments, how to implement them, and their role in creating smooth, scalable applications. So far, we covered the importance of sound effects in enhancing user engagement in Android applications. We explored the sound pool class for managing and playing short sound effects, and discussed the necessary steps for initializing and loading sounds based on Android version compatibility. Additionally, we covered how to play, stop, and manage sound effects for optimal user experience. Finally, we emphasized the role of sound in creating an interactive experience for users. Now we will talk about fragments, an essential feature that enhances app usability, particularly in complex layouts and navigation. Let's start with the basics. A fragment represents a reusable portion of your app's user interface. You can think of it as a mini activity that lives within an activity. Activities host fragments, which can have their life cycles and be easily combined to create multi-pane UI designs. A key advantage of fragments is their ability to adapt to different screen sizes, allowing for tablet and phone layouts to be distinctly optimized. Think about a social media application where users can view their feed and a profile side by side on tablets, but see them one at a time on phones. This is where fragments shine, as they offer a way to display this content decisively. The typical approach is to create a fragment class that extends the fragment class, and you'll override the onCreateView method to define your fragment layout. Now let's see how we can implement a simple fragment in our Android application. Here, we define a class called SimpleFragment, which extends the fragment class. This setup allows our fragment to inherit the behaviors and functionalities necessary to function within an activity. The most crucial method we override is onCreateView, which is responsible for creating and returning the view hierarchy associated with the fragment. In this method, we utilize a layout inflator, which helps us inflate a layout resource file into the fragment. Specifically, we call the inflate method, passing in the layout resource our layout fragment simple, alongside the container view and a Boolean flag set to false. This approach effectively attaches the layout to its parent while letting us retain control over how it is displayed. By using this modular structure, we promote code reusability, making it easy to customize or test the fragment independently. Overall, this example lays a solid foundation for working with fragments in a dynamic and responsive user interface. Now let's see how we can implement the fragment container in our activities layout. We start by defining a frame layout, which serves as a placeholder for our fragments. This layout specifies an id fragment container, which will be used to reference this container programmatically. By giving it a width and height of match parent, we ensure that the fragment takes up the entire screen space available, allowing it to adapt to various screen sizes. Next, we will write the code needed to dynamically add our simple fragment into the frame layout. We begin by obtaining the fragment manager through the getSupportFragmentManager method, which gives us control over fragment transactions for the activity. Then we start a new transaction with beginTransaction, preparing to manipulate fragments. Now let's create an instance of our simple fragment and add it to our fragment container using the add method, specifying the container id we defined earlier. Finally, we use commit to finalize and execute the transaction, making our fragment visible on the screen. This process allows us to efficiently manage the fragments within our application, adapting as needed for different user interactions and layouts. Now let's see how we can implement fragment transitions to enhance the user experience in our application. To achieve smooth animations when a fragment appears or disappears, we can utilize the setCustomAnimations method within our fragment transaction. By calling this method, we can define animation resources for both entering and exiting fragments. In our case, we'll specify the sliding animation for entering the fragment from the left and exiting to the right using the provided Android resources. This small addition will give our transition a dynamic feel, making it more engaging for users as they navigate through different sections of the application. It's important to place this line of code before calling the add method, which is responsible for introducing the fragment into the activity's user interface. By doing so, we ensure that the animations are applied correctly at the moment the fragment is added. Utilizing these built-in animations not only adds polish to the app, but also enables developers to create customized animations that resonate with their application's overall design and user experience goals. Next, we will write the following code to manage the lifecycle of our fragment, focusing on resource management during its visibility. The onStart method is overridden here, and in this method, we call superOnStart to ensure that any necessary operations from the super class are performed before we initiate our actions. This is the right moment to fetch data or start animations, as the fragment is becoming visible to the user. Then we override the onStop method, which is called when the fragment is no longer visible. Again, we first call superOnStop to maintain the chain of lifecycle events. Afterward, it's crucial to release any resources or stop any ongoing processes to prevent memory leaks. By utilizing these lifecycle callbacks effectively, we can ensure that our app remains responsive and efficient, handling resource management without unnecessary strain on the system. This attention to detail is key in Android development, particularly when dealing with fragments that might frequently appear and disappear based on user interactions. Now let's see how we can implement the fragment navigation within our application. The code provided illustrates how to replace a currently displayed fragment with a new details fragment when the user selects an item from a list. First, we create an instance of the detail fragment class, which we want to display. This is crucial because each fragment represents a distinct part of the user interface and its associated behavior. Next, we utilize a fragment transaction to manage this change. By calling the replace method, we tell the fragment manager to remove the existing fragment within the specified container, in this case, the fragment container, and insert the new detail fragment in its place. This ensures that the user's view is updated dynamically without the need for a full activity restart. Additionally, using add to backstack null allows users to navigate back to the previous fragment with the back button, providing a seamless and intuitive user experience. This method is instrumental in maintaining the app's navigation flow, allowing for a smooth transition between different screens or views within your application. Overall, this code segment encapsulates a key aspect of efficient fragment management and navigation in Android development. Now let's take a look at how fragments can communicate with each other through the hosting activity. First, we define an interface called onItemSelectedListener, which will facilitate the interaction between the list fragment and the activity. This interface declares a method named onItemSelected, which takes a string parameter representing the selected item. Next, in the list fragment, whenever an item is selected, we notify the activity by invoking the listener's onItemSelected method with the selected item as an argument. This step establishes a callback mechanism, allowing the activity to respond to user actions within the fragment. Now let's implement the corresponding functionality in the activity. The main activity class implements the onItemSelectedListener interface, which requires it to provide an implementation for the onItemSelected method. In this method, we create a new instance of the detail fragment and pass the selected item to it by using a bundle. The activity then initiates a fragment transaction to replace the current fragment with the detail fragment, while also adding the transaction to the back stack. This allows for smooth navigation, letting users return to the previous fragment seamlessly. Through this architecture, we maintain a clean separation of concerns, enhancing both code organization and maintainability. Now let's see how we can implement the viewModel pattern within a fragment to manage UI-related data. We start by creating a class, myViewModel, that extends the viewModel class. This class contains a private instance of mutable live data string named data, which will hold our UI data. the getData method is designed to check if the data has been initialized. If not, it initializes it and calls the loadData method to populate it with initial data. In the loadData method, we simulate fetching data by setting the value of data to sample data. This encapsulation ensures that our data management is tidy and efficient. Now let's discuss how we will utilize this view model in our fragment. Inside the fragment, we initialize myViewModel using ViewModelProvider, allowing us to share the ViewModel instance across the fragment lifecycle. We then observe the data with getData. By setting up an observer, any changes in data will trigger the UI to update automatically. This approach streamlines data management and enhances user experience by ensuring that the UI stays in sync with the underlying data. To wrap up, we have covered a lot of ground regarding fragments in Android development. You learned what fragments are and how they help create a more flexible and efficient user interface by managing modular components. We also explored how to create, add, replace, and manage the lifecycle of fragments, which is essential for resource management. Fragments also enhance navigation within applications and facilitate communication between different parts of your UI, promoting better design patterns. Finally, integrating ViewModel and live data into your fragments allows you to maintain UI data seamlessly, enhancing the user experience significantly. Understanding fragments is foundational in creating robust Android applications. While they might seem a bit complex at first glance, mastering them will open up numerous possibilities for building rich user interfaces that are responsive and adaptable. So get out there, implement some fragments in your project, and watch as your app comes to life. Now let's explore the concept of using multiple fragments in Android applications. This is a significant topic, as it enables developers to create versatile and dynamic UIs that considerably improve user experience. So far, we learned about fragments, which are reusable portions of a user interface in Android applications, allowing for modular and adaptable layouts. We explored how to create and manage fragments, including the lifecycle dynamic addition to activities and transitioning between them. Additionally, we discussed the importance of communication between fragments through the hosting activity and how to integrate ViewModel and live data for efficient data management. Overall, fragments play a crucial role in enhancing navigation and user experience in Android applications. Now, we will discuss how to use multiple fragments effectively to create more complex and dynamic UIs. Now let's take a look at the list fragment class, which is designed to handle the display of a list of items. This fragment utilizes a recycler view to showcase the items efficiently, which is essential in modern app development due to its capacity to manage large datasets with minimal performance issues. The fragment includes an inner interface, onItemSelectedListener, that must be implemented by the hosting activity. This setup facilitates interaction between the fragment and the activity, allowing the activity to respond when an item in the list is selected. Next, we will implement the onAttach method, which connects the fragment to the activity. Here, we ensure that the activity correctly implements the onItemSelectedListener interface. If it does not, an exception is thrown, ensuring robust error handling. In onCreateView, we inflate the fragment's layout and initialize the recycler view. The adapter for the recycler view is set up to use a lambda expression, which calls the callback method whenever an item is clicked. This ensures that the correct position of the selected item is communicated back to the activity, paving the way for displaying relevant details in the detail fragment. Next, we will write the detail fragment, which will display detailed information about the selected item from the list fragment. In this fragment, we define a text view that will be used to show the details. The key method here is onCreateView, where we inflate the fragment's layout and initialize the text view. This method ensures that the fragment's view is correctly set up when it becomes visible. Now let's implement the updateDetail method, which takes a string parameter and updates the text view with the new detail. This method enables the fragment to respond dynamically to user selections from the list, ensuring that the detail view reflects relevant information based on the user's actions. Next, we will configure our main activity, which will serve as the host for both the list fragment and detail fragment. In the onCreate method, we check if the activity is being created for the first time. If so, we use the fragment manager to replace the specified container views with instances of the list fragment and detail fragment. This setup establishes the initial user interface and paves the way for seamless interactions. Additionally, we implement the onItemSelected method to handle item selection events from the list fragment. This method retrieves the detail fragment instance and calls its updateDetail method with the relevant information, ensuring that the detail view is appropriately updated based on user selections. With this configuration, you've created a cohesive interface that effectively utilizes fragments to enhance user experience. Now let's implement functionality in the detail fragment that allows users to navigate back to the list fragment seamlessly. We will achieve this by adding a button that triggers the back navigation when clicked. In the onViewCreated method, we first retrieve the button using its ID. This button is essential because it serves as the user interface element for the back action. Next, we set an onClickListener for the button. This listener will call the onBackPressed method of the hosting activity when the button is clicked. By invoking onBackPressed, we effectively pop the current detail fragment off the fragment back stack, returning the user to the previous fragment, which is the list fragment. This method ensures that the navigation feels natural and fluid, providing an intuitive user experience without compromising on code simplicity or efficiency. By implementing this feature, we enhance the usability of our app, allowing users to quickly return to their lists or prior selections without additional complexity. Now let's implement the shared view model, which will play a critical role in maintaining user selections across configuration changes. This class extends viewModel, enabling it to store data that can survive configuration changes such as screen rotations. Inside the class, we define a mutable live data string instance named selected, which holds the currently selected item. The method selectStringItem allows us to update the value of selected whenever a user makes a choice. To retrieve the stored item, we provide a getSelectedItem method that returns live data string. This encapsulation is vital because it ensures that our UI can observe changes in the data without being tightly coupled to the data source, thus promoting a clean architecture. The shared view model acts as a shared resource between fragments and the activity, providing a seamless flow of information that enhances user experience. By using this view model, even when the activity is recreated due to configuration changes, the user selection is preserved, allowing the application to maintain its state efficiently. Now let's implement the synchronization of our fragments with the view model. We begin by defining a shared view model class that will manage the communication between our list fragment and detail fragment. This view model holds a mutable live data object to store the currently selected item, which allows the fragments to effectively share data without directly interacting with each other. Next, in the list fragment, we will initialize the shared view model within the onCreate method. This ensures that we obtain a reference to the activities view model, which is crucial for sharing data across fragments tied to the same activity lifecycle. When an item in the list is clicked, we invoke the callback method to notify the hosting activity and also update the selected item in the view model using the select method. In the detail fragment, we will observe the live data from the view model. By setting an observer on the selected item, we ensure that the UI updates automatically whenever a new item is chosen in the list fragment. This approach not only maintains data consistency through configuration changes, but also enhances the robustness of the application, allowing for seamless data flow between fragments. In conclusion, using multiple fragments within an activity not only enriches user experience by providing a coherent navigation model, but also aligns closely with the principles of efficient coding practices in Android development. As demonstrated, whether it's handling interactions, accounting for configuration changes, or allowing for better state management through view model, fragments facilitate a modular approach that can significantly enhance your application's structure. As you continue building and testing your applications, embrace the power of fragments to create interfaces that are as dynamic as your user interactions. Now let's take a look at how to implement the ViewPager in your XML layout file. The ViewPager widget allows users to swipe left and right to navigate between fragments, which in this case will display images. The provided XML configuration defines a ViewPager that takes up the full width and height of its parent, ensuring an immersive experience while swiping through the content. Next, we will write the adapter class named ImagePagerAdapter, extending FragmentPagerAdapter. This adapter is responsible for providing the images to the ViewPager by managing fragment instances. Each fragment is created with an image URL from the provided list, ensuring that the ViewPager can display the correct image at the selected position. The getItem method creates a new instance of image fragment with the appropriate URL, while the getCount method returns the total number of images available. Now let's implement the image fragment class. This fragment will inflate a layout containing an image view, where the actual image will be displayed. Using a static method, we can pass the image URL as an argument through fragments bundle. Inside the onCreateView method, we utilize Glide to efficiently load and display the image in the image view, ensuring smooth loading and performance. Next, we will specify Glide as a dependency in the build Gradle file. This step is essential for image loading, as it manages the complexity of image management and caching for us. Lastly, we will write the main activity class where we initialize the viewPager and set up our adapter with a list of image URLs. This final piece connects everything together, leading to a functional image gallery that users can easily swipe through. Now let's see how we can enhance our viewPager implementation by adding a tab layout for visual feedback on the current page. First, we need to include the material components library in our build, Gradle file, which provides us with the tab layout functionality. This is an important addition, as it will help visually indicate which page the user is currently viewing. Next, let's implement the UI by adding a tab layout above the viewPager in our XML layout file. This placement ensures the tabs are easily accessible, enhancing navigation. The tab layout will allow us to create a series of indicators, like dots or numbers, that reflect the pages within our viewPager. Now let's consider how to link the tab layout to the viewPager. By calling setup with viewPager, we establish a direct connection that enables the tab indicators to automatically update according to the page being displayed as the user swipes through. To further improve user experience, we can customize the tabs by creating a custom layout, allowing for the inclusion of icons or specific styling. This customization makes the navigation not only functional but visually appealing. After defining the custom layout in XML, we will implement a method that inflates this layout for each tab, thus providing users with a distinct and engaging interface as they explore your content. Now let's implement a custom page transformer to enhance the swipe experience in our viewPager. We'll create a class called ZoomOutPageTransformer, which implements viewPager page transformer. This transformer allows us to change how pages are displayed during the transition. Within the transformPage method, we first retrieve the width and height of the page. Depending on the position of the page, we can manipulate its properties. For pages outside the visible range, we set the alpha to 0, making them fully transparent. For visible pages, we calculate a scale factor that reduces their size as they move away from the center of the screen, and we adjust their margins to create a zoom-out effect. This helps create a more dynamic interaction. Pages that are swiped away will appear smaller, while the current page is scaled up to maintain user engagement. Lastly, we need to set this transformer to the viewPager by calling the setPageTransformer method after we've established our adapter. This simple addition allows users to enjoy a unique visual experience as they navigate through images. Next, we will write the layout for our full-screen image activity, which is essential for displaying images in full-screen mode. This layout consists of a single image view that fills the entire screen, ensuring that users have a close-up view of the images. To achieve this, we set the layout width and layout height to match parent, and utilize the scale type property set to center crop, which ensures the image covers the entire image view without distortion. Now let's implement the image tap functionality in the image fragment. To allow users to open an image in full screen mode, we add a click listener to the image view that holds the image. When the user taps the image, an intent is created to start the full screen image activity. The image URL is passed along with the intent, ensuring that the full-sized image can be fetched correctly. Finally, in the full screen image activity, we retrieve the image URL from the incoming intent. In the onCreate method, after setting up the content view, we use Glide to load the image into the image view. This integration provides a smooth experience for users, enabling them to appreciate the details of the images just like they would in a photo. Now let's dive into building an advanced app with a navigation drawer, aptly named Where It's Snap. This exciting development project aims to provide users with an intuitive and smooth interface, making navigation easy and user-friendly. In this lesson, we'll explore how to implement a navigation drawer in Android, which allows for convenient access to different sections of the app. So far, we learned about creating dynamic user interfaces in Android using fragments, exploring fragment transactions, and maintaining state with viewModel and live data. We implemented paging and swiping functionality with the viewPager widget, enhancing user experience by allowing smooth navigation through images. Additionally, we integrated a tab layout for visual feedback, added custom tab layouts, and improved swipe animations with page transformers. Finally, we provided a feature to view images in full-screen mode for a better user experience, resulting in a more engaging photo gallery application. Now, we will focus on enhancing our app with a navigation drawer, allowing easy access to different features and functionalities. Now let's implement the XML layout for our navigation drawer. This code starts with a drawer layout, which serves as the root container for our app. Inside the drawer layout, we have a frame layout designated for the main content. This is where your fragments will be displayed as users navigate through different sections of the app. The navigation view is included for the sliding menu that provides access to various features. Notice how we specify the Android layout gravity attribute as start, ensuring that the drawer opens from the left side of the screen. We also define a header layout and a menu resource file to customize the navigation items. The header layout can include user information, while the menu resource will populate the drawer with selectable items, each intended to facilitate navigation. It's crucial to ensure these components are correctly wired up in your activity. This layout lays the foundation for a smooth user experience, allowing seamless transitions between the different sections of your app as users interact with the navigation drawer. Next, we will write the menu resource file that defines the items in our navigation drawer, which is crucial for providing users with accessible navigation options. This file is typically named navmenu XML and includes a series of item elements, each representing a unique action that can be selected from the drawer. In our implementation, each item is assigned an ID, such as navCamera, navGallery, navSlideshow, and navTools, allowing us to identify which action the user has selected later in our code. Each item also has a title, which is the text that will be displayed to the user in the navigation drawer. This structure not only makes it easy to handle user interactions with these items, but also maintains a clear and organized representation of the available navigation options. Defining these items in a separate resource file helps keep our code modular and user-friendly, allowing for easy updates and maintenance as the app evolves. As we progress, we will connect these menu items with specific functionalities in our application, enhancing the user experience by facilitating smooth navigation. Now let's implement the functionality to handle user interactions in our navigation drawer. To begin, we define our main activity, which extends app compatibility. Here we declare two essential components, drawer layout and navigation view, which will manage the navigation drawer and the menu items respectively. In the onCreate method, we initialize these components by linking them to the respective views defined in our XML layout. Next, we implement the navigation item selected listener for our navigation view. This listener allows us to respond to menu item selections appropriately. Within the listener, we set up a switch statement that checks the ID of the selected menu item. Each case corresponds to a navigation action, such as opening the camera or gallery. After executing the relevant behavior for the selected item, we ensure a smooth user experience by closing the drawer using drawer layout close drawer. The method returns true to signify that the item selection has been handled effectively. This structure not only allows for easy navigation between different app functionalities, but also lays the groundwork for further enhancements, such as fragment transactions for dynamic content display. Now let's implement the following code to ensure our navigation drawer can be opened and closed with a simple gesture. The Action Bar Drawer Toggle class provides a convenient way to manage the drawer's state and synchronize it with the action bar icon. By instantiating toggle and passing in the current activity context, the drawer layout, and the string resources for the open and close drawer states, we bind the toggle to the drawer. Next, we need to register the toggle as a listener for the drawer layout by adding it as a drawer listener. This will allow it to respond to user interactions. After setting up the listener, calling ToggleSyncState helps ensure the action bar icon reflects the correct state of the drawer, automatically updating to show the hamburger icon when the drawer is closed and the arrow icon when it is open. Remember that this integration requires appropriate string resources defined in strings, XML, as these are crucial for providing the user with accurate navigation feedback. This setup enhances the usability of your app's navigation drawer, making transitions smooth and intuitive for users. Next, we will write the implementation for the camera fragment, which serves as the centerpiece for handling camera functionality within our app. This code defines a new class, Camera Fragment, that extends the Fragment class, allowing it to be part of the Android framework for user interface components. In the onCreateView method, we override the default behavior to specify what view the fragment should display. Here, we utilize the layout inflator to inflate the specific layout defined in the XML file, Fragment Camera, which houses all the UI elements for this particular fragment. By passing in the container and false, we ensure that the fragment's layout is properly integrated into the existing view hierarchy, but does not attach it to the container immediately. This makes it flexible for later additions of UI components or logic, particularly when we decide to extend the fragment with actual camera functionalities. This foundational setup allows for modular code, maintaining separation of concerns, and ensuring that each aspect of your app can be developed and modified independently as your project progresses. Next, we will implement the onNavigationItemSelected method in our main activity, which will handle the selection of menu items from the navigation drawer. This method begins by defining a variable, selectedFragment, that will hold the instance of the fragment that corresponds to the user's selection. As the user chooses an item from the menu, we use a switch statement to check the item's ID, associating each case with a specific fragment, such as camera fragment, gallery fragment, slideshow fragment, and tools fragment. If the user selects a valid menu item, selected fragment will be assigned the appropriate fragment instance. Once we determine which fragment to display, we perform a fragment transaction using the Fragment Manager. The beginTransaction method is called to initiate the transaction, and we replace the current view inside the content frame with the newly selected fragment. This replacement is finalized with the commit method, ensuring the transition takes effect. Finally, we close the navigation drawer using Draw Layout, Close Draw Gravity Compat, Start, creating a seamless user experience as they navigate throughout the app. This functionality not only enhances navigation, but also makes the interaction dynamic and engaging. Now let's implement the following code snippet to enhance our navigation drawer experience with visual feedback. In the onNavigationItemSelected method, we first define a transition object by inflating a predefined transition from our transition resources. This transition, specified in an XML file, will dictate how the visual elements animate between fragment changes. Next, we initiate the transition using Transition Manager BeginDelayedTransition, targeting the content frame where our fragments are displayed. By wrapping the fragment replacement logic within this transition, we create a smooth animation effect as the user navigates through different sections of our app. This not only improves the aesthetics of our navigation, but also provides a sense of continuity, making the transition visually appealing. Using shared element transitions adds a professional touch to the app's functionality, enhancing user engagement and making navigation feel more fluid. This small yet impactful change can significantly improve the overall user experience, encouraging users to explore different features within where it's Snap. Now let's implement the following style attributes for our navigation drawer in the Styles XML file. By adding these attributes, we ensure that our navigation drawer aligns with the material design guidelines, enhancing its visual appeal. The color primary dock, and color accent items will define the primary colors for the navigation drawer, giving it a consistent look with the rest of our application. These styles will not only improve the aesthetics of the drawer, but also contribute to a seamless user experience. When implemented, users will notice a more polished interface that maintains visual coherence throughout the app. Additionally, customizing the header layout with profile images and user information further personalizes the experience, making the app feel more engaging. Overall, these style enhancements are a crucial step in refining the appearance of the navigation drawer and building a visually appealing application. This visual styling, combined with the previously discussed functionalities, will create an immersive and user-friendly environment, reflecting a modern design approach in your app. Now let's implement a user feedback feature using snack bars. This will help users understand their actions within the app, such as confirming a navigation event. The code we will write utilizes the snackbar class from the material design library. By calling snackbar make, we create a new snackbar instance, specifying the view to bind it to, the message to display, and the duration the snackbar should be visible. In this case, we are binding the snackbar to our drawer layout, meaning that the feedback will appear in relation to the navigation drawer. The message provided, navigated to camera, serves to inform users about their recent action when they switch to the camera fragment. The snackbar length-shot parameter sets the visibility duration to a brief moment, ensuring that the message is delivered without disrupting the user experience. Finally, we call show on the snackbar to display it on the screen. This implementation not only enhances the overall user experience by providing immediate feedback, but also keeps users engaged and informed about their navigation choices within the app. In summary, we have covered how to implement a navigation drawer in our Where It's Snap app, enabling users to switch easily between different sections. We defined the layout and menu items, set up click listeners, and implemented fragment transactions to offer effective navigation. Additionally, we enriched the user experience by applying styles, visual feedback transitions, and providing user interaction confirmations. As we continue to build our app, we can integrate more advanced features and functionalities that will take our user experience to the next level. In the next lessons, we will delve into integrating additional functionalities that will make our app even smarter and more user-friendly. Stay tuned as we take the next steps towards building a fully featured app. Next, we will write the following method called dispatchTakePictureIntent, which is essential for capturing images using the device's camera. This method first initializes an intent with the action type, MediaStar, action image capture. This action indicates that we want to capture an image, triggering the camera application. To ensure we do not encounter any errors, we include a check using resolveActivity, which verifies that there is an application available to handle this intent. This step is crucial as it prevents our app from crashing if no camera app is found on the device. If an appropriate application is available, we call startActivity4Result with our intent, along with a unique request code, requestImageCapture. This function prompts the system to start the camera application, enabling the user to take a photo. Once implemented, this method allows us to seamlessly integrate image capturing functionality into our app, enhancing user engagement by facilitating easy image creation. With this foundational step in place, we can further expand our application's capabilities to include handling the captured images in subsequent methods. Now let's see how we can implement the onActivityResult method to handle the image captured from the camera. In this method, we first call the superclass's implementation to ensure that any necessary processing occurs. Next, we check if the request code matches our predefined constant, requestImageCapture, indicating that the result is indeed from our camera operation. Additionally, we confirm that the result code is ResultOK, which tells us that the image capture was successful. If both conditions are met, we then proceed to retrieve the image data contained in the extras of the intent. Here, we extract the bitmap image using dataGetExtras, allowing us to pull out the thumbnail image generated by the camera. Finally, we display this bitmap in the image view that we have designated in our layout, ensuring it appears to the user. Remember, it's crucial to have defined the image view in your activity layout for this to work correctly. This method effectively integrates image capturing into our app's workflow, providing a seamless experience for users. Next, we will write the layout code for our image capturing feature. Here, we utilize a relative layout to organize UI components effectively. Within this layout, we define an image view, which will be crucial for displaying the image that users capture. The image view is set to match the width of its parent layout while adapting its height to contain the image, ensuring it maintains its aspect ratio by utilizing wrap content. We also include a content description, which is important for accessibility purposes, allowing screen readers to identify what the image represents. Below the image view, we place a button, enabling users to trigger the image capture action. The button is appropriately labeled with a string resource for localization and presents an intuitive interaction. Importantly, we link the button's click event to the dispatchTakePictureIntent method through the onClick attribute. This setup seamlessly connects the button's action to our image capture logic, making it user-friendly and straightforward. Overall, this layout establishes a clear and functional interface for users to engage with the image capturing process in our application. Now let's see how we can implement the functionality for allowing users to select an image from their gallery. We begin by defining a method called OpenGallery. Inside this method, we create a new intent with the action type, intent, actionPick, which prompts the system to display a pick a dialog for selecting an item from a list. Next, we specifically use MediaStar, images, media, external content URI as the content URI, which directs the intent to the device's image gallery. This setup ensures that the user can only pick images, providing a controlled and reliable selection experience. After preparing the intent, we call startActivity4Result, passing in our gallery intent and a request code, requestImagePick. This request code will help identify the result when we handle the return data. By invoking this method, we launch the gallery and wait for the user's selection. This seamless integration allows us to expand our app's image capturing capabilities, making it user-friendly as the functionality now includes both capturing images and selecting them directly from the gallery. Now let's take a look at the implementation of the onActivityResult method for selecting an image from the gallery. This method is crucial for handling the results of activities that you initiate, such as when a user picks an image from their device. The first line ensures that the superclass's implementation is called to maintain the activity lifecycle properly. Next, we check if the request code corresponds to our defined constant, requestImagePick, and if the result indicates a successful operation with ResultOK. This ensures that we only process valid selections. If these conditions are met, we then extract the image URI from the returned intent data. The URI serves as a reference to the selected image, allowing us to access it easily. Finally, we set the image URI on our image view. This step invokes the setImageURI method, which efficiently retrieves and displays the image at the specified URI in our user interface. By implementing this code, we allow users to seamlessly choose an image from their gallery and display it within our app, enhancing user engagement and functionality. Next, we will write the following code to integrate the ucrop library, which allows users to edit and crop their images before display. First, you need to add the ucrop dependency in your build, Gradle file. This is essential as it enables the library's functionalities in your Android project. Now let's implement the method called startCrop. This method takes a URI parameter named sourceURI, which represents the image that has just been captured or selected. Inside the method, we specify a destination URI that points to where the cropped image will be saved. In this case, we are saving it in the cache directory of the application as cropped image, JPG. Next, we initialize the ucrop instance using ucrop of sourceURI destination URI, allowing us to define the cropping operation. With the with_aspect_ratio 1:1 method, we set the aspect ratio of the crop, which provides a perfect square crop for consistency in image dimensions. Finally, by using with max result size 500, we limit the maximum dimensions of the cropped image to ensure it does not take up excessive resources. Once configured, we invoke start this to launch the cropping activity, letting users seamlessly tailor their images before they are displayed in the app. Now let's see how we can handle the result from the ucrop activity. In this section of the code, we override the onActivityResult method to manage different types of results based on the request codes we've defined earlier. We start by checking if the request code matches either the image capture or image pick request. If it does, we have already handled those scenarios, so we simply take note of that to keep our code organized. Next, we focus on the ucrop request crop. When the cropping request is successful, indicated by the result code, we use the utility ucrop getOutputData to retrieve the URI of the cropped image. This URI points to the new image that has been cropped based on the user's adjustments. We then set this URI to our image view, ensuring that the cropped image is displayed smoothly to the user. This step not only enhances the usability of our application, but also allows users to work with images tailored to their preferences, paving the way for a more interactive and satisfying experience in our app. And there you have it, our implementation is looking solid. We are able to capture images, select them from the gallery, and even crop them before displaying. Just to recap, we began by discussing how to initiate intents to capture images using the camera, how to handle the images in the result callback, and how we expanded our functionality by allowing users to select images from their gallery. To sum it up, the Android intent class simplifies the way we interact with built-in applications like the camera and gallery. The MediaStore class serves as a gateway for accessing these functionalities, and through these processes, we've added significant features to enhance the usability of our app. You're now more equipped to implement image capturing in your Android applications. As with any development tasks, experimentation is key. Don't hesitate to test out variations of code examples and adjust parameters to suit your application's needs. Remember, the world of Android development is vast, and there's always something new to learn. Creating applications that provide significant features often requires a robust way to manage, store, and filter substantial amounts of data. In the world of Android development, Sqlite databases are a crucial part of this process. Utilizing Sqlite in your Android applications can empower you to handle data efficiently, fostering enhanced user experiences through optimized data storage and retrieval. So far, we covered how to implement image capturing in Android applications using the intent class, including how to launch the camera, handle captured images, and display them in an image view. We also explored selecting images from the gallery and introduced image cropping to enhance user experience. This foundational knowledge equips you to integrate robust image handling features into your applications. Now we will cover how to use Sqlite databases to manage the data your apps generate. When we talk about databases, we are referring to structured collections of data that can be easily accessed, managed, and updated. Think of them as digital filing cabinets, where each drawer represents different types of data, and each file within those drawers is an individual record. For Android applications, Sqlite is the lightweight database engine that closely interacts with Java, allowing for seamless data management. Before diving into coding, let's familiarize ourselves with SQL and Sqlite. SQL, or Structured Query Language, is the standard language for interacting with databases. Sqlite, on the other hand, is a special version of SQL designed specifically to work within mobile and embedded devices, like your Android phone. It's serverless, requires no configuration, and it stores its data in a single file. In our discussion about Sqlite, we can't ignore the importance of certain SQL commands that facilitate database management. For instance, the insert command is used to add new data to your database. The select command is essential for retrieving data, while delete removes specified data entries. Understanding these commands will enable you to build effective queries for your app. Now let's implement the Data Manager class, which is essential for handling our Sqlite database interactions. This class extends Sqlite Open Helper, giving us the ability to create and manage databases efficiently. We start by defining our database name, my database, DB, and its version, initializing these constants for easy reference. In addition, we declare constants for our table name, users, and the columns that will store user data, including an ID, name, and age. Next, we implement the constructor, which calls the superclass constructor with the defined database name and version. This setup ensures that our database is correctly initialized when we create an instance of Data Manager. Moving on, we override the onCreate method, where we write the SQL statement to create the users table with appropriate field types. This method is called the first time the database is created, establishing the necessary framework for our data storage. Lastly, the onUpgrade method handles updates to the database structure. If the database version changes, it drops the existing table and calls onCreate to set up a new one, ensuring our app always operates with the latest structure. Now let's implement a method to add new users to our database. The insertUser method takes in the user's name and age as parameters. First, we get a writable instance of the database using this getWriteableDatabase to ensure we can modify the data. Next, we create a new content values object, which acts like a mapping of column names to their respective values, essential for preparing our data for insertion. We populate this content values object by specifying the column names, column name, and column age, and their corresponding values, the arguments passed into the method. Once our values are in place, we call the db insert method to execute the SQL insert command. This method is crucial as it directs the database to add a new row to the users table, using our content values as the source. Finally, we close the database connection with dbClose to free up resources and ensure proper interaction with the database. This simple yet essential method allows our application to seamlessly add user entries whenever needed, contributing to efficient data management throughout our app. Next, we will implement a method to retrieve all users from the Sqlite database. This method is defined within the Data Manager class and is crucial for accessing the stored data. We begin by obtaining a readable instance of the Sqlite database using this getReadableDatabase, which prepares the database for read operations without modification risks. Now let's take a look at how we execute the SQL query. Using db_raw_query, we can run a select statement to fetch all records from the users table. The method returns a cursor object, which is an excellent tool for iterating over the results, essentially acting like a pointer that helps us navigate through each row returned by our query. The power of a cursor lies in its ability to provide access to the data structure transparently, allowing us to extract specific column values from each row, like user names and ages, during our app's runtime. This method is a vital piece of functionality as it enables applications to display or process user data effectively, enhancing the overall user experience by integrating data retrieval seamlessly into our application workflow. Now let's implement the functionality to retrieve and display user information from our Sqlite database. We start by calling the getAllUsers method from our Data Manager class, which returns a cursor object that contains all entries from the users table. The cursor acts like a pointer that allows us to navigate through the results efficiently. Next, we enter a while loop that continues as long as there are more entries to process in the cursor. For each entry, we extract the user's name and age using the appropriate column indices defined in the Data Manager class. By leveraging methods like getString and getInt, we can retrieve data in the correct format. After extracting this information, we use the log class to print it to the console, which provides a simple validation of our database operations, ensuring everything is working correctly. Finally, it's essential to close the cursor once we're done to free up resources. This approach offers a straightforward means of verifying that our data retrieval operates as intended while laying the groundwork for incorporating this data into the UI later. Now let's implement the method that enables users to search for specific records in our Sqlite database. We will create a method called searchUserByName within our Data Manager class. This method accepts a single parameter, name, representing the name of the user to search for. Inside this method, we initiate a readable instance of our database by calling this getReadableDatabase. This is crucial as we want to retrieve data without making any modifications to the database. We then construct a SQL select statement with a where clause to filter the results based on the provided username. To prevent SQL injection attacks, we utilize a placeholder. in the SQL query, which we bind to the actual name parameter using an array. The method executes the query using db raw query, which returns a cursor object containing the results. This cursor can be traversed to access the specific records that match the search criteria, allowing for efficient and safe data retrieval based on user input. This method enhances the overall functionality of our application, making it easier for users to find relevant records. Now let's implement the method for deleting user records based on their names. The deleteUserByName method allows us to remove specific entries from the database efficiently. Within this method, we first obtain a writable instance of our database using getWritableDatabase, which ensures we can make changes. Next, we use the delete function of the Sqlite database class, where we specify the table from which we want to delete records, in this case, table name. The condition for deletion is defined using a where clause, which checks for the column name that matches the user-provided name parameter by incorporating the placeholder. In the SQL command and supplying the actual value as an argument, we not only maintain code clarity, but also enhance security by preventing SQL injection. Finally, after executing the deletion, it's crucial to close the database connection with dbClose, which helps release resources and avoid potential memory leaks. This method will effectively remove any record that corresponds to the specified name from the user's table, making it a simple but powerful function for record management. Through this guided approach, you've gotten a comprehensive overview of how to manipulate Sqlite databases in Android apps, from setting up your database, through adding, retrieving, searching, and deleting records. There's much more to explore in the Sqlite ecosystem, including concepts like data indexing, transactions, and schema migrations. Knowing how to efficiently store and manage data is key to creating performance-oriented, robust applications. Each step we covered lays the foundation for building more complex functionality tailored to your application's needs while ensuring a smooth experience for your users. The possibilities are endless, and with Sqlite at your disposal, you have a powerful tool to tackle them all. Remember to keep experimenting, improving your SQL skills, and refining your application design as you delve deeper into the world of Android development. Welcome everyone. Today, we're diving into adding a database to our app, where it's Snap. This process will significantly enhance its capabilities and provide a robust way to manage our photos and tags. So far, we learned about the importance of managing data in Android applications using Sqlite, which serves as a lightweight database engine for seamless data handling. We explored fundamental SQL commands like insert, select, and delete, allowing for effective database management. Additionally, we implemented a data manager class to facilitate database interactions, including methods for adding, retrieving, searching, and deleting user records. This knowledge sets the stage for building robust applications that offer optimized data handling and user experiences. Now we will cover how to incorporate fragments, interfaces, and Sqlite to give where it's Snap the functionality it truly needs. Let's get started. Now let's implement the photo class, which serves as a model for our photos in the app. This class will have private fields that hold essential details, a title for the photo, a URI pointing to its storage location, and 3 tags for better organization. Using URIs instead of storing images directly helps maintain a clean and efficient database structure, as we only store the image's file path. We provide getter and setter methods for each field, allowing other parts of our application to access and modify these properties securely. This encapsulation promotes a clear interface and keeps the internal representation hidden, an important aspect of object-oriented programming. By structuring the photo class this way, we create a comprehensive model, paving the way for data interactions with our local database and ensuring that we can manage our photos and their attributes efficiently. Next, we will move on to the Data Manager class, which will manage all interactions with the Sqlite database, including creating tables and handling database operations for our photos and tags. Next, we will implement the Data Manager class, which is essential for managing our Sqlite database interactions. This class sets up the database by defining some crucial constants, such as the database name, version, and the table names for photos and tags. Now let's take a look at the constructor. It initializes the database by creating an instance of a helper class called Custom Sqlite Open Helper, which is responsible for creating the database tables. Inside the Custom Sqlite Open Helper, the onCreate method is significant as it defines how our tables are structured. Here we have 2 tables, one for photos and another for tags. Each table is created with specific columns, such as image title, URI, and tags for the photo table. This structured design ensures that we can efficiently store and retrieve the necessary data. Next, we should enhance our Data Manager class with methods to add and retrieve records. For instance, the addPhoto method allows us to insert a new photo into the Photos table. Using content values, we create a key value pair representing the photo's properties, which will be inserted directly into the database. Similarly, with methods like getTitles and getTags, we can retrieve relevant data using SQL queries, enabling effective data management within our application. By equipping the Data Manager class with these functionalities, we lay a solid foundation for robust data handling in our app. Next, we will write the method addPhoto in our Data Manager class, which is crucial for adding new photo records to our Sqlite database. This method takes a photo object as a parameter and uses the content values class to prepare a collection of key value pairs that represent the photo's data. Each piece of information from the photo object, such as the image title, storage URI, and tags, is placed into content values by calling the relevant getter methods. This structured approach simplifies data insertion. Once the content values instance is populated, the insert method of the Sqlite database object is called, utilizing our defined table for photos. This method inserts the values into the appropriate columns of the database table. By organizing the photo's data in this way, we ensure that our database receives structured and easily accessible information, allowing us to manage photo entries effectively. This method serves as an entry point for interaction with the database, enabling the app to update its records seamlessly as users add new images. Now let's create a method to retrieve photo titles using a database query. In this implementation, we define a method called getTitles within our Data Manager class. This method utilizes the raw query function of the Sqlite database class to execute a SQL command that selects both the unique ID and the image title from the photos table. The SQL query constructed is straightforward. It fetches the columns id and image title from the table photos. The use of raw query is particularly effective here, as it allows us to retrieve a cursor object that represents the result set of the query. This cursor can then be iterated over to access each title and ID as needed. Utilizing a cursor not only provides a clear structure to our database results, but also offers efficient data retrieval that is crucial for application performance, especially when dealing with multiple records. Next, we will implement a method to handle tag retrieval from our database. This is crucial for maintaining and displaying tags effectively to users. We achieve this by creating a getTags method in the Data Manager class, which executes a SQL query using raw query. This query selects both the id and tag fields from the table tags, allowing us to fetch all the tags stored in the database. By encapsulating this functionality in a method, we streamline the process of accessing tag data, making it easy to manage tags throughout the application. When we call this method, it returns a cursor object, which serves as a lightweight interface for accessing the results of the database query row by row. This approach not only organizes our database interactions, but also enhances user experience by ensuring that tags can be retrieved and displayed efficiently whenever needed, helping users navigate their tagged photos with ease. Now let's see how we can implement the button functionality for saving photos in our capture fragment. We begin by defining an on-click listener for the Save button, which triggers when the user taps it. Inside this listener, we first check if the image URI is valid, ensuring that we have a photo to save. If the URI is not null and not equal to an empty URI, we proceed to create a new photo object. Here, we set various properties of the photo object, including the title and storage location from user inputs, as well as the associated tags. Once we have populated the photo object with all necessary details, we utilize our Data Manager instance to add this photo to our Sqlite database with the addPhoto method. This method handles the database insert operation using the content values class, which helps structure our data in a key value pair format suitable for database entries. Finally, we provide feedback to the user by displaying a toast message confirming that the photo has been saved, or an error message if no image was present for saving. This implementation not only allows for seamless data handling, but also enriches the user experience within our application. Next, we will implement the titles fragment to manage the display of photo titles. This class extends list fragment, allowing us to leverage the built-in functionality for presenting a list of items. Inside the onCreate method, we initialize a Data Manager instance to access the Sqlite database, fetching the titles with getTitles, which returns a cursor. We then set up a simple cursor adapter, which binds the data from the cursor to a simple list view layout. The first parameter specifies the context, the second defines the layout for each list item, and the third is the cursor with the data. The from and to parameters indicate which column from the cursor to display and the corresponding view in our layout. By calling setListAdapter, we link the adapter to our fragments list, enabling the display of titles. The onListItemClick method captures user interactions, where we move the cursor to the selected position and obtain the corresponding ID of the photo. This ID can then be passed to other activities or fragments for further actions, facilitating a seamless user experience as they navigate through their photo collection. Next, we will implement the ActivityComs interface, which is essential for communication between the titles fragment and the main activity. This interface defines a single method, onTitlesListItemSelected, that takes an integer ID as a parameter. The purpose of this method is to facilitate interaction, allowing the selection of a title in the titles fragment to be communicated back to the main activity. By implementing this interface in main activity, we can effectively handle the selected titles, which then allows us to update the UI accordingly. When a title is selected, the onListItemClick method in the titles fragment will retrieve the corresponding database ID and invoke the onTitlesListItemSelected method. This action creates a connection between our fragment and the main activity, enabling it to manage which photo is displayed in the view fragment. By defining this communication layer through the ActivityComs interface, we ensure a seamless flow of information across the different components of our app, ultimately enhancing the user experience. Now let's implement the onTitlesListItemSelected method in main activity, which plays a key role in fragment management. This method will be triggered when a user selects a title from the list. Within this method, we start by creating a bundle object, which acts as a container for passing data between fragments. Using the putInt method, we store the position of the selected item, allowing us to track which photo the user wants to view. Next, we instantiate a new view fragment and set the arguments we've packaged in the bundle using fragment setArguments args. This is crucial because it allows the view fragment to access the selected position to retrieve and display the corresponding photo. Finally, we initiate a fragment transaction using getFragmentManager, begin transaction, which is essential for replacing the current fragment. With the replace method, we define that the fragment in the RID fragment holder, the designated area in the layout, will be swapped out for our newly created view fragment. This operation is finalized with commit, which commits the changes made during the transaction, ensuring that the user interface is updated to show the selected photo. By following these steps, we successfully integrated a database into Widgets Snap, supporting photo management and tagging functionalities. In summary, we have constructed a solid foundation for managing photos using Sqlite, built the corresponding classes, and linked everything with fragments. Now you have a powerful tool to manage your photo collections within your Android app. I encourage you to explore adding features, such as filtering by tags or displaying more details about each photo. That's it for today. Don't forget to like, subscribe, and comment below with your questions or what you want to see next. Integrating Google Maps and GPS locations can transform your application from a simple photo-sharing platform into a remarkable tool for navigation and discovery. Today, we will delve into how to leverage these technologies, guiding you through setting up your own application that harnesses the power of GPS and Google Maps. So far, we learned about enhancing our app, Widgets Snap, by integrating an Sqlite database for efficient photo and tag management. We created a photo class to structure our photos with relevant fields and a data manager class to handle database interactions, including adding and retrieving data. We also developed user interfaces using fragments to manage photo saving and displaying titles effectively. This foundation allows for further enhancements, such as filtering and displaying more photo details. Now we will talk about integrating Google Maps and GPS locations, allowing our app to provide geolocation features and much more. Next, we will adjust our app's configuration settings in the build, Gradle file. Here, we specify essential details like the application ID, minimum and target SDK versions, version code, and version name. This setup ensures that our app meets the necessary requirements for running on Android devices, while also targeting the features introduced in newer Android versions. Setting the target SDK version to 22 allows us to leverage the Marshmallow runtime permissions effectively, providing a smoother user experience. Once that's done, we need to request the necessary location permissions in the Android manifest XML file. This is crucial for allowing our application to access the device's location services. By incorporating the user's permission tags, we ensure that our app can retrieve both find and cost location data, as well as access the internet for additional functionality. This step is vital to ensure users grant the app appropriate permissions to operate smoothly. Now let's implement a straightforward layout for the main activity using layout main, XML. This layout consists of 3 text view components designed to display the latitude, longitude, and source of the location data obtained through GPS. Implementing this layout will facilitate user interaction by clearly presenting critical location information as the app functions. Now let's implement the Java code in main activity Java that forms the backbone of our location-aware application. We start by defining the main activity class that extends the activity and implements the location listener interface. This enables our activity to listen for location updates from the location manager. Next, we declare member variables for the text views that will display the latitude, longitude, and the source of our location. Additionally, we introduce the location manager and a string variable for the provider, which will help us identify the best way to access location data. In the onCreate method, we initialize the views by linking them to their corresponding layout elements. This sets up our UI. We then acquire a reference to the location manager service to fetch location data. By creating a criteria object, we call getBestProvider to select the most suitable provider based on the parameters we've established. Following this, we check for the last known location from the provider and update our UI with this data if it's not null. This initial setup provides a framework for dynamically displaying real-time location information, forming a crucial step in enhancing user experience in our app. Now let's see how we can implement location updates in our app. To actively listen for the user's location, we utilize the requestLocationUpdates method within the onResume Lifecycle method. This ensures that every time the app comes back into view, we start requesting location updates. Specifically, we ask for updates every 500 milliseconds or whenever the location changes by at least 1 meter, allowing us to keep our location data fresh and responsive. To manage battery efficiency, we also override the onPause method to stop these updates when the user navigates away from the app. This approach helps preserve battery life while ensuring we only use resources when necessary. By implementing these 2 methods, we smoothly integrate location tracking into our app, providing users with frequent updates as they navigate through the application. This code forms the backbone of our GPS functionality, allowing us to create a dynamic and engaging user experience based on real-time location data. Next, we will implement the required methods from the location listener interface to manage real-time location updates. The key method, onLocationChanged, is invoked whenever the device's location changes. In this method, we extract the latitude and longitude from the provided location object. This is crucial for displaying the user's current location on the app's UI, ensuring users receive immediate feedback about their whereabouts. Now let's see how we can handle other scenarios related to location updates. The onStatusChanged method notifies us of changes in the availability of the location provider. We'll update the UI to reflect this change, ensuring the user is informed in case of any interruptions in the location service. Similarly, the methods onProviderEnabled and onProviderDisabled allow us to respond when the GPS provider is enabled or disabled. Here, we will simply update the UI to notify users of the current source of the location data, creating a seamless and informative experience within our application. This robustness in handling location updates significantly enhances the app's responsiveness and user engagement. Now let's implement the Google Maps API key in our project. We start by adding a string resource in the Google Maps API XML file, where you'll place your actual API key. This key is critical as it authenticates your app with Google services, ensuring you can access map functionalities. By developing within Android Studio, the IDE automatically generates this XML file, making it easier to manage API keys. Next, we need to ensure that the Google Play Services library is included in your project. This library provides the necessary tools and components to integrate Google Maps into your application seamlessly. Check your SDK manager within Android Studio to verify that you have the latest version installed, as up-to-date dependencies are essential for optimal performance. Now let's get down to coding our Google Maps integration. We'll create a new activity called MapsActivity and set up a layout that utilizes a support map fragment. This fragment will hold our map and allow us to interact with it programmatically. By implementing the onMapReady callback interface in our Maps activity, we can perform operations on the map once it is fully loaded, providing a dynamic and interactive experience for the user. Now let's implement the layout for our Maps activity using the Maps activity XML file. Here, we will define a fragment that will serve as a placeholder for our Google map. The fragment tag is used to instantiate a support map fragment, which is essential for displaying maps in Android applications that utilize the Google Maps Android API. We specify the XML namespace attributes for Android and tools, setting the layout width and height to match the parent view, ensuring it takes up the entire screen. The Android id attribute assigns a unique ID at +idMap to our fragment, which will allow us to reference it in our activity code. The tools context attribute points to our map's activity, indicating that this is where the fragment resides. Finally, the Android name attribute refers to the fully qualified class name of the support map fragment. This setup ensures that when we later manipulate the map programmatically, we have the correct connection established between our layout and the fragment that will display the map. With this fragment configured, we can now proceed to implement the functionality to interact with the Google Map in our Maps activity. Now let's implement the essential functions for Google Maps within Maps activity. We begin by declaring a class that extends fragment activity and implements the onMapReady callback. This allows our activity to respond once the map is ready for use. Inside the onCreate method, we set the content view to the layout that includes our map fragment and obtain a reference to the support map fragment from the fragment manager. This fragment will take care of displaying the map in our application. Next, we call getMapAsyncThis, which is crucial as it triggers the asynchronous loading of the map. Once the map is ready, it will call the onMapReady method. Here, we will work with the Google Map object to interact with the map's features. In onMapReady, we define a lat.lng object, which represents the geographical coordinates of Silicon Valley, and use this to add a marker on the map. Additionally, we use moveCamera, allowing the camera to focus on Silicon Valley, providing a better user experience by directing the view to our point of interest. This integration enriches our application with location-based functionality, enhancing its interactivity and usability. Finally, we have our application connected to both GPS and Google Maps. Running the app will display a map pinpointing the specified location, alongside the appropriate latitude and longitude information displayed from your device's GPS source. In this tutorial, we journeyed through integrating Google Maps and GPS into your Android application, enhancing the overall functionality from a simple photo-sharing app to a dynamic location-based experience. With the groundwork laid, you can explore adding more features, such as routing capabilities and custom markers. Make sure to check the Google Maps documentation to discover more powerful functionalities you can incorporate into your app and unleash the full potential of your location-aware application. Now that we know how GPS and Google Maps work together, we will look at another approach to using them. This segment will focus on upgrading Sqlite to include functionality for locations and maps. We aim to create a robust application where users can not only take photos, but also associate them with geographical data, thus enhancing interaction. So far, we learned about enhancing our app, where it's Snap, by integrating an Sqlite database for managing photos and tags, structuring photos with a photo class, and creating user interfaces with fragments. We then explored GPS technology, set up a new project to access location services, and implemented code for real-time location updates. Finally, we initiated Google Maps integration, including creating a new activity, setting up the layout, and displaying a marker on the map. This foundation allows us to develop a more dynamic location-based application. Now let's explore how we can set up our Sqlite database to manage photo and location data effectively. We create a database helper class that extends Sqlite Open Helper, which facilitates the creation and management of our database. Inside, we define constants for the database name, version, and table structure. Notably, we introduce new columns for latitude and longitude in the Photos table, which allows us to store geographical information alongside each photo. Next, we implement the onCreate method, where we create the Photos table with the relevant columns. This method is triggered when the database is initially created. We use SQL commands to define the structure of our table, ensuring the id column serves as the primary key, while latitude and longitude are defined as real numbers to accurately handle geographical coordinates. In the onUpgrade method, we ensure that the app can gracefully handle database version changes. If a new version is detected, this method drops the existing Photos table and calls onCreate to create the updated structure. This setup is crucial for maintaining the integrity of our data and allows for easy functionality enhancements in our application as development progresses. Now let's see how we can implement location tracking in our application using the Google Play services. The first step involves setting up a fused location provider client, which provides a simple way to interact with location services. We initiate this client with the context of our application. Next, we create a location request object to specify how often we want to receive location updates. In this case, we set an interval of 10 seconds for high-accuracy location updates. To handle these updates, we define a location callback, where we override the onLocationResult method. This method gets invoked whenever there is a new location available. If the location result is null, we simply exit to avoid errors. Otherwise, we loop through the received locations, extracting the latitude and longitude values from each location object. These coordinates are logged for now, but it's important to note that we have the ability to save this information alongside photos in the Sqlite database. Finally, we begin the location updates by calling request location updates on our fused location client, ensuring we are continuously receiving location updates as the user interacts with the app. Now let's implement the functionality to capture a photo alongside its geolocation data in our application. We begin by defining the capture photo method, which initiates the camera action to take a picture. Here, we create an intent to launch the camera and check if there's an available application to handle this intent. If everything is set up correctly, it calls start activity for result, allowing us to receive the image data once the photo is captured. Next, we need to handle the result of the photo capture in the onActivityResult method. After confirming that the activity result corresponds to our photo request, we extract the image data from the incoming intent. The image is processed and saved to storage using a helper method that returns the path of the saved image. At this point, it's crucial to retrieve the latest GPS coordinates, which we will use to link the photo with its geographical location. We access the Sqlite database and create a content values object to hold the image path and latitude and longitude values. Finally, we insert this data into the photos table of our database, ensuring that each photo is effectively associated with its geographic context, thereby enhancing our application's functionality. Now we will implement the functionality to display the captured photos on a map using Google Maps. First, we define an onMapReady method, which is automatically called when the Google Map is ready for interaction. Within this method, we initialize our Google Map object and invoke the loadPhotosOnMap method to load the markers based on the photos, coordinates stored in our Sqlite database. Next, we focus on the loadPhotosOnMap method. Here, we establish a connection to the database and execute a query to retrieve all photo records. As we iterate through the results, we extract the image path, latitude, and longitude for each photo. Using the retrieved latitude and longitude, we create a new lat.lng object representing the geographical position of each photo. We then add a marker to the map at this position, setting the title of the marker to the image path. This effectively displays the photos on the map, allowing users to see where each photo was taken. Finally, we ensure to close the cursor and database connection to maintain resource efficiency in our application. This sets the stage for users to create a visual narrative of their photo-taking adventures. Now let's implement the functionality that allows users to interact with map markers and view the photos associated with them. We begin by setting a click listener for the markers added to the map. When a user taps on a marker, the listener triggers an event that retrieves the image path from the marker's title. This image path is essential, as it tells the app which photo to display. Next, we create an intent that serves as a bridge to launch a new activity, specifically Photo Detail Activity, where the photo will be shown. By passing the image path as an extra in the intent, the newly started activity gains access to the correct image, enabling it to present the user's memory linked to that geographical point. The return value of true from the onMarkerClick method indicates that we've handled the marker-click event, preventing the default behavior of the map clicking interaction. This enhancement enriches user experience, facilitating easy navigation through their memorable photos contextualized by their locations. In doing so, we make the application not just functional, but also engaging and intuitive for users who want to revisit their captured moments. As we wrap up our tutorial on integrating location and maps with Sqlite in our app, let's reflect on what we've covered. We began by enhancing the database schema to include geographical data, enabling the application to store information related to the location where each photo was taken. We captured GPS data in real time whenever an image was snapped, and saved that alongside the image in our Sqlite database, ensuring that each photo has contextual geographical information. Furthermore, we brought a visual representation of user memories by loading the photos onto Google Maps, allowing users to navigate their experiences graphically. Lastly, we made the map interactive, enabling users to view their captured moments just by clicking on the corresponding markers. With this, we have created a location-based application that offers a rich user experience and a way to effectively manage and remember their memories through geographic context. In the following sessions, we'll expand upon these ideas, perhaps by adding even more features such as filtering photos by location or integrating with social media for sharing. The possibilities are. In today's lesson, we will dive into the fascinating world of localizing Android applications with multiple languages. The purpose of this exercise is to ensure that our app is accessible to as many users as possible, transcending language barriers, while demonstrating how Android's localization functions rather than focusing on the intricacies of translation. So let's get right into it. So far, we covered enhancing our app, where it's Snap, by integrating an Sqlite database to manage photos with geographical data, allowing users to associate images with their locations. We explored GPS technology and implemented real-time location updates while capturing photos, storing both images and their corresponding coordinates in the database. We then set up a Google Maps integration to display user photos based on their geographical context and introduced interactivity, enabling users to view their photos by clicking on map markers. This foundation creates a location-based application that enriches user experience and memory management. Now we will cover the process of making our app multilingual by adding support for languages such as Spanish and French. With the increasing global user base of mobile applications, understanding how to localize your app can significantly improve user engagement and satisfaction. Let's start examining how we can effectively localize our app. Next, we will write the following strings in our strings XML file, which will be located in the recently created values folder for Spanish localization. This mockup defines a set of string resources that will be used throughout your application. Each string resource is encapsulated within string tags, where the name attribute serves as a unique key that links the string to the corresponding element in your application. For instance, we have defined app name with the value localización, which represents the name of your application in Spanish. Similarly, movie title is set to Lo cual vinto si levo, translating the title of a popular movie into Spanish. The other strings, line 1 and line 2, are also direct translations of important phrases that enrich the app's text content. When configured correctly, this structure allows Android to automatically fetch and display these strings whenever a Spanish-speaking user interacts with your app. This not only enhances the user experience by providing relevant content in their native language, but also demonstrates the app's commitment to accessibility in a global marketplace. Next, we will implement the following French translations in the strings XML file within the values.fr folder we just created. This XML file is crucial for providing localized string resources that will be displayed in the app when the device's language setting is set to French. In the resources tag, we begin by defining several string elements that correspond to key phrases within our application. The name attribute serves as the identifier that links each string to specific parts of the app code. For instance, we have app name set to localization, which reflects how the app will be identified to French-speaking users. Additionally, the movie title, Importé par l'event, is provided to ensure that users see the title in their native language. Furthermore, important dialogue lines have been translated, such as line 1, which reads, Ret si vous allez ou origi, que dois-je faire, and line 2, translated to Franchement marchia, je n'y donne pas une putain. These strings allow us to maintain the narrative context of the original content while making it accessible to French speakers. This process enriches user experience by ensuring that the content feels native and relatable to a broader audience. To see this in action, run your app with the usual setup in Android Studio. Switch the device to Spanish. If you are using an emulator, you can often find localization settings under the Settings app, or you can use a custom locale app to simulate the device's language. Change the locale to Spanish, and upon reopening your application, you should see the translated string resources appear. Pretty neat, right? If you want to switch back to English, you can follow the same steps to set the language back to the default locale. This functionality underscores how seamless it is to inbuild localization in your Android application without needing significant code alterations. Now let's take a look at how to organize your drawable resources for localization in your Android application. As we discussed, localizing an app isn't just about translating text, but also includes adapting images and other media to fit various cultural contexts. In this regard, you will create separate directories under the Res folder specifically for localized image resources. To implement this, begin by constructing a drawable directory for your default images. Inside this folder, you will create additional subdirectories named Drawables for Spanish and Drawable.fr for French. Here you will place the respective images that are culturally relevant and appropriate for Spanish and French users. For instance, you might name a localized Spanish image localized image, PNG, and the French version image localisé, PNG. When your application runs, Android will automatically select the correct image from these folders based on the current locale set by the user's device. This approach not only enriches the user experience, but ensures that all visual elements align with the language and culture of the user, making your app feel more personal and accessible. While automated translations can sometimes suffice for simple applications, they often lack the cultural nuance that can make or break user engagement. A common recommendation is to use a professional service or native speakers for translating critical texts, especially if your application has a significant presence in a particular market. This due diligence in localization not only focuses on the words used, but also on the context and sentiment conveyed, which is paramount for user satisfaction. Now that we've roughed out the basics of Android localization, another great resource to explore is the Android developer documentation. It's filled with insights and more advanced techniques on how to handle localization effectively, including plural handling or formatting strings for your various locales. In conclusion, making an app multilingual is a vital step in expanding your audience and improving user engagement globally. By simply creating additional resource folders, we can tailor the experience for users across different languages and cultures effectively. So don't overlook localization in your app development. It can set you apart in a crowded market. Stay tuned for our next session, where we'll tackle more advanced Android concepts to further enhance our skills as mobile developers. Happy coding, and good luck in localizing your application. In this video tutorial, we will explore how to create a simple game using Android's threading capabilities and the Canvas class for graphics. This session promises to be engaging as we work independently to create something exciting with code. So far, we have learned about enhancing our app by integrating an Sqlite database to manage photos with geographical data, allowing users to connect images to locations. We've implemented real-time GPS updates and Google Maps integration to create an interactive location-based application. Additionally, we introduced localization in our Android app by adding support for Spanish and French, ensuring a seamless user experience across different languages. In this lesson, we will dive into the realms of threading, drawing, and touch handling, culminating in the creation of a simple Pong game. Get ready to embrace the world of game development on Android. Now let's take a look at setting up our game thread within the GameView class. In this code snippet, we initialize a thread named mGameThread, which handles the game loop, maintaining a smooth experience by running independently of the main UI thread. When the game resumes, we set the mPlaying variable to true and create a new thread that runs the run method. This method contains an ongoing loop that continues as long as mPlaying is true, allowing us to frequently check for user inputs, update game states, and render graphics. Next, when we pause the game, we set mPlaying to false and attempt to join the thread to ensure it properly terminates. This is essential to avoid potential issues like trying to access the drawing or game logic when the game is not running. In the run method, we set the foundation for our game loop where all the action happens. This endless loop keeps the game responsive, enabling updates and rendering to happen seamlessly. By encapsulating this logic within a dedicated thread, we ensure that our game remains smooth and responsive, even as various events take place. Now let's see how we can set up our drawing environment within the GameView class. We begin by declaring two key variables, a canvas object named mCanvas and a paint object, mPaint, which will be used for drawing. In the constructor for the GameView class, we call the superclass constructor and initialize mOurHolder to manage the drawing surface. Here, we also create an instance of mPaint and set a default color of white to ensure our drawings are visible against the black background. Next, we will implement the draw method. This method is where the rendering takes place every time the game needs to refresh the visuals on the screen. Before we start drawing, we check if the surface of mOurHolder is valid, which ensures that we only attempt to draw when we can safely access the canvas. We lock the canvas to prevent other threads from accessing it, allowing us to clear the previous frame and draw the current state of our game objects, such as the paddle and ball. After drawing, we unlock the canvas and post the updates, so the player sees everything on the screen. This process is vital for creating a fluid and responsive gaming experience. Now let's implement the onTouch event method to handle touch interactions from the player. This method allows us to detect where the user touches the screen, which is crucial for controlling the paddle in our Pong game. In our code, we start by checking the action of the touch event. When the action is action down, which indicates that the user has started touching the screen, we need to determine the touch's horizontal position. If the touch occurs in the right half of the screen, we proceed to set the paddle's movement state to paddle right, making the paddle move to the right. Conversely, if the touch is detected on the left side, we set the movement state to paddle left, moving the paddle in the opposite direction. This creates a responsive touch control mechanism that enables intuitive gameplay. When the user lifts their finger off the screen, indicated by Action UP, we set the paddle's movement state to paddle, STOPPED, halting its movement. Returning true from the method ensures that we successfully handle the touch event, allowing our game to react appropriately to user inputs. Next, we will write the ball class, which is essential for controlling the game's ball mechanics. This class has private attributes that define the ball's rectangular shape through a rectef object, as well as its x and y velocity, indicating how fast and in which direction it moves across the screen. In the constructor, we initialize the rectef object to define the ball's size and set both the x and y velocities. Here we have assumed a constant speed, but these values can be altered to change the game's dynamics. Now let's implement the update method, which plays a critical role in the ball's movement. This method calculates the new position of the ball based on its velocity and the frames per second, FPS, to ensure smooth movement across different devices and frame rates. It updates the rectangle's left and top attributes to reflect the ball's new position on the screen, while also keeping the right and bottom attributes consistent with the ball's size. This continuous update will allow the ball to move fluidly within the game environment, contributing to the core gameplay mechanics as it interacts with the paddle and the screen edges. Now let's implement the core of our game loop within the run method of the GameView class. This method is critical as it defines how our game will continuously update and render its graphics. Inside a while loop, we check if the game is still playing, indicated by the mPlaying boolean. This loop runs repeatedly to create the game cycle. Next, we measure the start time of each frame to calculate the elapsed time for performance assessment. If the game isn't paused, we call the update methods for both the ball and paddle. This step is essential as it updates their positions based on the frame rate, ensuring smooth movement regardless of device performance. Then we invoke the draw method to render the newly updated positions onto the screen. After rendering, we compute the time taken to complete this frame. By checking if this time is greater than or equal to 1 millisecond, we can accurately calculate the frames per second, FPS. This measurement helps maintain consistent and responsive object movements, making the game feel fluid and engaging for players. As we conclude this session, we hope you feel more confident about creating simple games in Android using threads and Canvas. We've covered essential concepts, including how to create and manage threads, handle graphics with Canvas and Paint, and respond to user interactions. In our next tutorial, we could extend our game with additional features like scoring, power-ups, or even different game levels. Always keep experimenting, as practice makes perfect. Now go forth and code your game. To publish applications on Google Play, developers need to follow a structured process that ensures their app meets Google's guidelines for quality, security, and user experience. In this section, we will walk through the step-by-step instructions to successfully publish your application on the platform, including preparing your app, creating a developer account, and managing your app after it is published. Now let's implement the following configuration in our build, Gradle file to create a signed APK for our app. This snippet establishes the signing configurations necessary to authenticate a release version of the app. In the Android block, we're defining a new signing configs block where we create a release signing configuration. Here we provide the essential details such as the key alias, which identifies our key within the key store, and the key password needed to access it. We also specify the path to the key store file with store file, ensuring that the application can locate this file when it's time to sign the APK. The store password protects the key store itself. Additionally, we set up the build types block, which allows us to specify different configurations for various build types. Here, we define the release build type and link it to our previously defined signing configuration. By doing this, when we generate a signed APK, it will automatically use the specified signing configurations, providing the necessary security and authentication for our application when it's published on Google Play. Now let's take a look at how to format your app's title and description for submission to the Google Play Store. The provided example showcases a title and a well-structured description for an app called Crazy Fun Pong. A strong title is essential as it should be concise and directly reflect your app's functionality, making it easier for potential users to find it in search results. Next, we will write the description, which serves to entice users while providing them with a clear understanding of what your app offers. The description begins by inviting users to experience a nostalgic classic with a modern twist. we highlight key features, such as exciting multiplayer capabilities and unique power-ups, ensuring these points catch the user's attention. The use of bulleted lists helps present information in a clear and digestible manner, making it easy for users to scan through the features. Finally, a compelling call to action encourages users to download the app, reinforcing their motivation to engage with your offering. By implementing such a well-crafted title and description, you enhance your app's visibility and appeal, ultimately increasing the likelihood of downloads. Next, you'll upload your APK. In the Release Management section, click on App Releases. Choose whether you want to deploy your app to production, closed testing, or open testing. An open testing rollout can be beneficial if you want to gather preliminary user feedback before making your app available to the general public. Once you select the appropriate rollout, you will be prompted to upload your APK or app bundle. If there are any issues with the APK you uploaded, Google will notify you at this stage, indicating what needs to be corrected. After successfully uploading your APK, you need to fill out the details section. This includes the app category, contact details, and privacy policy URL, if applicable. It is crucial to set up these details accurately, as they not only help Google evaluate your app, but also ensure compliance with the regulations surrounding app publishing. Following the details setup, you will need to provide the content rating. Google recommends using their questionnaire that helps determine the appropriate age rating for your app based on its content. Accurate ratings are vital because they guide users in making informed decisions about installing your app. After addressing the content rating, it's time to set up pricing and distribution. You can choose to distribute your app as a free or paid application. If you're opting for a paid app, consider pricing it competitively. Google allows you to select the countries you wish to distribute your app in. While setting up these parameters, it's wise to review Google's developer policy compliance. This ensures that your app adheres to the platform's guidelines regarding user data, intellectual property, and acceptable content. Any violations might result in your app being rejected or removed from the store. Once you have completed all the necessary sections and are satisfied with how everything appears, you can submit your app for review. Google generally takes a few hours to a few days to review new submissions, depending on several factors, including the app's complexity and the current volume of submissions. Make sure to keep an eye on the Google Play console, as they will provide feedback if any adjustments are needed for your app. Once your app is approved, you will receive a notification, and it will be live on the Play Store. Congratulations, you've officially published your app. However, the journey doesn't end here. Monitoring your app's performance is crucial. The Google Play console provides insights into user feedback, crash reports, and download statistics. Utilize these tools to understand how your app is performing and to identify areas for improvement. Implementing updates based on user feedback is vital for maintaining your app's relevance and improving user satisfaction. And don't forget to promote your app through social media and other channels to maximize visibility. Now let's see how we can integrate Firebase Analytics into our app to gain valuable insights into user interactions. First, you'll need to declare the necessary dependency in your build, Gradle file. This is essential for incorporating Firebase Analytics SDK, which provides the tools you need to track user behavior effectively within your application. In the Dependencies section, you will write a line to implement the Firebase Analytics library. By including implementation com Google Firebase Analytics, latest version, you ensure that your app can access the latest version of the Firebase Analytics features. This addition enables you to monitor a variety of user engagement metrics, such as user retention rates and screen view times, which are crucial for understanding how users interact with your app. With Firebase Analytics integrated, you can continuously evaluate user behaviors and preferences, allowing you to make informed decisions about future updates and enhancements. The data you collect will play a significant role in guiding the evolution of your app, helping you to adapt to changing user needs and improve overall user experience. In conclusion, publishing an application on Google Play involves several meticulous steps: preparing your app, creating a developer account, uploading your APK, ensuring compliance with Google's guidelines, and maintaining ongoing user engagement. With every update and improvement, you pave the way for a better experience for your users and higher visibility for your app. The journey of app development is ongoing, filled with opportunities for creativity and innovation. With dedication, passion, and knowledge, you can build an amazing application that attracts users and stands out in a competitive market. Continue honing your skills and have fun in the